GCE Advanced Level Chemistry Practical Series, experiment number 35, experimental determination of the acidic basic neutral nature of aqueous solutions of salt by testing pH. So now let's take a look at the aims of this experiment. So the aim of this experiment is to classify given salts as acidic, basic or neutral by referring to the pH value of the aqueous solution. So throughout this experiment, students, we are going to be measuring the pH value of different salt solutions, and based on the pH value, we are going to classify them as acidic salts, basic salts and neutral salts. Salts are derived from the neutralization reactions between acids and bases. Salts are solid crystalline ionic compounds that are composed of cations and anions. They have high melting points. Now students, when you are talking about different types of salts, the salts are consisting of cations and anions. Cations are positively charged ions and anions are negatively charged ions. So they are attracted to one another through forces of or electrostatic forces of attraction, and we call this ionic bonding. As you know, ionic compounds have a very strong ionic lattice. So when you're trying to melt these ionic compounds that are in solid form, when you're trying to melt them, you would require a really high amount of energy to break this ionic bond and transform the solid ionic compound into molten state. So when you're turning a solid ionic compound to a liquid, you will require a really high amount of energy, and you can actually observe that these require really high amount of energy by observing their melting temperatures. Melting temperatures are really high. So this is because, students, again, these ionic compounds, they have very strong forces of attraction holding these ions together, or in other words, the ionic bonding is very strong and they have a very strong ionic lattice. In order to break this and turn the solid into a liquid, it would require a really high amount of energy, and this is why the melting temperatures of ionic compounds are really high. So if you take sodium chloride, sodium sulfate, these kind of salts, they will have a really high melting temperature. And in the previous equations, we can very clearly see how this acid and base react. You can see HCl will provide chloride ions and sodium hydroxide will provide sodium ions, and sodium ions and chloride ions together will form sodium chloride salt. Apart from that, H plus from HCl and OH minus from sodium hydroxide, they will join together to form water, right? So the salt that is formed here is sodium chloride, and apart from that, water is also formed. When I talk about sodium sulfate, when you're reacting sulfuric acid with sodium hydroxide, we can see sodium ions come from sodium hydroxide and sulfate ions come from sulfuric acid, and these join together to form sodium sulfate. Along with that, H plus from sulfuric and OH minus from sodium hydroxide join together to form water. Now water is present here as a covalent compound. This is not an ionic compound. Water is covalent. You should know the structure of water by now. However, these salts that are produced here consist of ions, so therefore these are ionic compounds. Aqueous solutions of molten liquids of salts are strong electrolytes. So if you take aqueous sodium hydroxide, they actually exist in aqueous medium as sodium 1 plus aqueous ions and chloride 1 minus aqueous ions. Although we write sodium chloride aqueous together in one single formula, in the aqueous medium, the sodium ions and chloride ions are not always connected to one another. They are hydrated and they are going to be moving about in the aqueous medium. They are not always sticking together, right? Instead, each ion is surrounded by a layer of water, right? So water molecules are attracted to these charged ions and they form what is known as hydration sphere. and therefore they stabilize these ions, and these ions are now mobile or moving within the aqueous medium independently of one another. So students, these mobile ions that we have in aqueous medium can conduct electricity as they can carry a charge. So since they are mobile, then since they are not limited to one specific location, they can now move about carrying a charge. When it comes to ionic compounds that are in solid state these ions are held in place through our ionic lattice. So they are not mobile, they are not moving. However, when it comes to an aqueous medium, these ions are now in the aqueous medium. They are separated, right? So they are stabilized by formation of hydrogen spheres, and these ions are now mobile. They can move about independently of one another. They don't have to always interact with one another and stay close to one another. In aqueous medium, they are independent of one another, so they can actually move about without the influence of the other. So when it comes to aqueous sodium chloride medium, we have sodium ions and chloride ions separately present in aqueous medium, and they can conduct electricity. And when it comes to sodium chloride, if you apply enough heat, we can melt sodium chloride. We can form this very viscous molten liquid, which is sodium chloride molten liquid that is getting formed here. And in that liquid, you will have sodium ions and chloride ions. Over here, there is a small correction to be made. This is not aqueous. This is not aqueous sodium chloride. All the ions are going to be present in the liquid state. So, sodium ions and chloride ions here are again not held by a lattice. By providing heat and melting the solid, what we are doing is we are breaking the lattice. At that point, sodium ions and chloride ions are moving independently of one another here as well. So students, even a molten liquid has these charged ions that are mobile, so therefore it can conduct electricity. So we can say that aqueous solutions or molten liquids of salts are strong electrolytes. Now for it to be an electrolyte, you should have ions that are able to move about. So therefore, since the aqueous form of these solutions as well as the molten ionic salts are both containing ions that are mobile, we can say that these are strong electrolytes when you are considering both the aqueous solutions as well as molten liquids. The ions formed above reaction can act as mobile charge carriers. They can act as mobile charge carriers, and therefore they can conduct electricity. So that is why we call them strong electrolytes. And this dissociation of ions when it comes to aqueous medium is complete. It's 100% dissociation. It's not a partial dissociation. That's another reason why we can call aqueous solutions of ionic salts like this a strong electrolyte. Classifying salts as acidic salts, basic salts and neutral salts. Based on the way that constituent ions of salts undergo hydrolysis, salts can be grouped under three categories: acidic, basic and neutral salts. Based on how the salts are formed through reactions between acid and bases, we can categorize them into four types. So now there are mainly three types of salts: acidic, basic and neutral salts. But students, there are four main types of reaction that can produce these different types of salts. There are mainly four different types of reactions between acids and bases that can take place when it comes to producing these salts. So let's take a look at those types of reactions that produce these different types of salts. First one, a reaction between strong acid and strong base. Strong acid, strong bases. Normally students, whenever we react a strong acid with a strong base, we say the resultant salt is a neutral salt. Now we'll be learning about that in a second. And then we have strong acids reacting with weak bases. Now strong acid, weak base will react together to form acidic salt. So one way in which you can remember whether the salt is going to be acidic, basic or neutral is by observing which one out of these two reactants is strong. So we have weak base and the acid is the one that is strong. So therefore, students, we can assume that we can actually predict and say that the salt that is produced will be having acidic properties because the strong reactant here is the acid. We say the acid is strong. Now this is just a way of remembering the nature of the resultant salt. This is not the logic behind why the acid is or why the salt is acidic. This is just a way to remember or to predict whether the resultant salt is acidic, basic or neutral. Now we will explain in detail why the resultant salt is acidic, basic or neutral, but when you are trying to initially understand or initially remember whether the resultant salt is going to be acidic, basic or neutral, this method will help. Out of the two reactants, take a look at which one is having this term strong. So therefore, if the acid is the one that is having the term strong, then the salt is going to be acidic. If the base is the one that is having the term strong, then the salt is going to be basic. If both acid and the base are strong, then the resultant salt is going to be neutral, right? So we have strong acid, weak base reactions resulting in acidic salts. Weak acids and strong base reactions will result in basic salts. And we have weak acids and weak bases. Now weak acid and weak bases are slightly more complicated than the other three reactions. Now when it comes to weak acids and weak bases, when both acids and bases are weak, based on which weak acid or which weak base is relatively more stronger than the other. So out of these two reactants, based on which one is relatively more stronger than the other, we will determine the acidity, or it will determine the acidity or basicity of the salt that is produced. So although both of them are weak, if acid happens to be relatively stronger, slightly stronger than the base, then the resultant salt will be acidic. If the base is slightly stronger, although both of them are weak, if the base happens to be slightly stronger than the acid, then at that point the resultant salt is going to be basic. Now we can figure out whether these acids and bases are, whether one reactant is stronger than the other by observing their dissociation constants. We can observe the weak acids acid dissociation constant, which is referred to as Ka, and when it comes to weak bases, we can take a look at their base dissociation constant, which is Kb, right? Based on their numerical value, based on their magnitude, we can actually predict whether the salt that is going to be produced is going to be acidic or basic. Now let's move on to the next slide. Salts formed through reactions between strong acids and strong bases are neutral. Salts formed through strong acids and strong bases, right? Strong acids and strong bases. Strong acids and strong base reactions produce neutral salts. Neutral salts. Now students, we have to identify strong acids and strong bases. Otherwise, you wouldn't be able to make correct predictions. So strong acids. Now these are the strong acids that we will come across when we are working in the lab. We have HCl, which you already know. Apart from that, HBr and HI are considered to be strong acids. These are all hydrogen halides. You can see Cl, Br and I is there. However, HF is not there. Hydrogen fluoride is not there because a hydrofluoric acid is not considered to be a strong acid. Hydrofluoric acid is not considered to be a strong acid. You will see when we are discussing weak acids, you will see among them you will find HF. Apart from that, you know nitric and sulfuric acids. Nitric and sulfuric acids are going to be considered strong acids as well. And we have chloric and perchloric acids. Chloric and perchloric acids are also considered to be strong acids. And then we have strong bases. We have lithium hydroxide. So all these group 1 elements and their hydroxides are referred to as strong bases, all the way from lithium to cesium. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide and cesium hydroxide. These are all considered to be strong bases. Strong bases. Apart from that, starting from calcium hydroxide, strontium and barium hydroxide, these are referred to as strong bases as well. So group 2 hydroxide, some of them are listed here, and these ones are strong bases. And then we have in this case what you have here is there's a positive charge here. There is a positive charge here. Right, so we have tetramethylammonium hydroxide. Tetramethylammonium hydroxide, which is also considered to be a strong base. Right, so now after looking at all of these bases, we can now move on to the next slide. So now students, we come across some examples of strong acid, strong base reactions. Strong acid, strong base reactions. We have HCl, sulfuric, nitric, HCl again. So these are all strong acids. We discussed it a little while ago. Then we have sodium hydroxide, potassium hydroxide, all are group 1 hydroxides. And then we have calcium hydroxide, barium hydroxide. These are group 2 hydroxides. They are all strong bases. Now, when it comes to the first reaction, you can see HCl and sodium hydroxide is a well-known reaction for all the students from the beginning of advanced level. You know that this reaction is a reaction between a strong acid and a strong base. We would have spoken about this reaction multiple times when we are starting off A levels as well. And even during O levels, you would have seen this reaction. And you can see the resultant salt is sodium chloride, and as you already know, sodium chloride is a neutral salt. As you already know, sodium chloride is a neutral salt. So if you take a little bit of sodium chloride and if you dissolve it in water, the pH of water will not change. If you are dealing with distilled water at room temperature or at 25 degrees Celsius temperature, at that point distilled water will have a pH of 7, a neutral pH. If you dissolve sodium chloride in it, the salt will remain neutral. There will not be an increase or a decrease of the pH value because the salt that we add to this distilled water is also a neutral salt. It will not interact with the water molecules in a way that will cause a hydrolysis reaction. So therefore, there will be no hydrolysis reaction when we are adding sodium chloride to water. So therefore, students, sodium chloride is considered to be a neutral salt. And then we have potassium hydroxide reacting with sulfuric, forms potassium sulfate. So potassium ion comes from a strong base, sulfate ion comes from a strong acid. So when a salt is formed in this particular manner, with a cation coming from a strong base and an anion coming from a strong acid, the salt that is formed is going to be neutral. Something to keep in mind, right? So if you are, without giving you this equation, if you are only given potassium sulfate, you have to ask yourself, okay, we have potassium ions and sulfate ions. From where would the potassium ions come if you are talking about acid-base reaction producing this salt? If acid-base reaction happened to produce this salt, from which base would potassium come from? From the base, usually we consider it came from the base potassium hydroxide, which is a strong base, right? Potassium ions come from this potassium hydroxide strong base, and then sulfate ions could come from sulfuric acid, which is a strong acid. So this resultant salt, potassium sulfate, is a neutral salt as it is a product of a strong acid strong base reaction. We have calcium nitrate, calcium ions reacting with or calcium hydroxide reacting with nitric acid. Calcium comes from the strong base calcium hydroxide, nitrate ions come from the strong acid nitric acid. So the resultant salt is a neutral salt. And we have barium chloride. Barium came from the strong base barium hydroxide, and Cl came from the strong acid HCl or hydrochloric acid. So therefore, students, resultant salt that is formed is going to be neutral. Now we move on to a very important topic, hydrolysis of cations and anions. Hydrolysis of cations and anions. Now, when it comes to any salt that is present in aqueous medium, first these cations and these anions, they are going to be surrounded by water molecules. Now, first of all, students, you have to understand the water is a polar molecule. If this is a water molecule, right, you will have a partially positively charged end to the water molecule as well as a partially negatively charged end to the polar molecule, right? So usually the oxygen end of the water molecule is partially negatively charged, and hydrogen end of the water molecule is partially positively charged, right? So water molecule is a bent molecule, so it has a dipole movement, and you know, since each of the bonds are polar because of the electronegativity difference between hydrogen and oxygen, and because of the angle of the molecule or because of the shape of the molecule, water molecule has a net dipolar movement or dipole movement. So therefore, students, water molecule ends up being a polar molecule. It has partially positively charged and a partially negatively charged end. Oxygen end is partially negatively charged, hydrogen end is a partially positively charged end. So let's take a look at what happens when positively or negatively charged ions, when they come into the medium, right? So at this point, water molecules will get attracted towards the positively charged ion, directing their partially negatively charged water molecules or the partially negatively charged oxygen atom towards the positively charged ion. So this way, water molecules will align itself around the positively charged ion, causing a layer of water to be present around the positively charged ion. And this is referred to as hydration of the ions, and these water molecules that are aligned in a specific layer around the positively charged ion is referred to as a hydration sphere. And this could happen to negatively charged ions as well, but when it comes to negatively charged ions, we would note that it is a hydrogen end that aligns, or hydrogen end that gets directed towards the negatively charged ion, and the partial negatively charged oxygen end is pointing away from the negatively charged ion. Is that clear? So just like earlier, water molecules, not just one, there will be few water molecules that are aligning itself in this manner, completely surrounding the negatively charged ion, forming a hydration sphere. So apart from this, students, apart from this, some anions and cations undergo hydrolysis reactions. So what we saw over here is referred to as the hydration process. Apart from that, it can also undergo a hydrolysis reaction. So now let's take a look at what is written here. The salts formed through reactions between strong acid and strong bases such as sodium chloride, potassium sulfate, calcium nitrate and barium chloride are neutral in nature. This is because their cations and anions do not undergo, very important, do not undergo any hydrolysis reactions in water. Only thing that happens to these cations and anions is that they get surrounded by water molecules and they get hydrated. That's the only thing that takes place when it comes to these salts, right? The cations and anions will not undergo hydrolysis reactions. They only get surrounded by water molecules, they get hydrated, that's it. They do not undergo hydrolysis reactions. Now, cations are found in strong bases do not undergo hydrolysis reactions. So, some cations are given here. For example, sodium, potassium, calcium, barium, rubidium, cesium. Again, we have mentioned calcium here. Strontium, barium, and in this case, tetramethyl ammonium ions. Tetramethyl ammonium ions. Now, these ions will also not undergo any hydrolysis reaction. So, tetramethyl ammonium ions look like this: CH3, CH3, CH3. This is the Lewis structure. So, these type of ions do not necessarily undergo any hydrolysis reactions because they are coming from strong bases. And then we have anions. Anions that are stemming from strong acids do not undergo hydrolysis reactions. So, any anions that are found in strong acids like chloride, we have bromide, iodide, right? We have the list: sulfate and nitrate, chlorate, perchlorate. These ions will not undergo hydrolysis reactions. They will therefore not cause the pH of the solution to change. If any of these ions, or whenever we are talking about a salt, if either the cation of the salt or the anion of the salt, or sometimes both the cation and the anion of the salt, can undergo hydrolysis reactions. Now, if they undergo hydrolysis reactions, at that point, pH of the solution can change. But if both the cation and the anion are not undergoing any hydrolysis reaction, that means pH of the solution is not going to be altered. Now, neutral salts form through reactions between strong acids and strong bases. Salts are formed through reaction between strong acids and strong bases are neutral. Ions found in these salts do not undergo any hydrolysis reaction in aqueous medium. So, we are going to be, again, this is something that we have stated earlier as well. So, now we are taking a look at the diagram over here, so we can actually understand what is meant in this particular statement. So, if you take a look at a sodium chloride solution at 25 degrees Celsius, sodium as well as the chloride ions. Now, each of these ions are not showing any further reactions with water. So, there are no hydrolysis reactions. So, therefore, the pH of neutral water, which is pH 7, will not be altered by these sodium or the chloride ions. And when you consider water, water has this equilibrium. Liquid water can turn into H3O plus and OH minus. It can turn into H3O plus and OH minus. Sometimes we also refer to this as H plus ions, right, which causes the acidity in water, and OH minus ions, which is responsible for basicity in water. But since water molecules, when they dissociate, form equal amount of H plus and OH minus, or H3O plus and OH minus, so we can see the number of H plus and OH minus ions in neutral water is going to be equal. So, therefore, there is no acidity or basicity. We say water is going to be neutral in pH, right? So, if when we add an acid, what happens? This H3O plus concentration will elevate, and because of that, we will have a higher H plus concentration than the OH minus concentration. So, the medium will be acidic, right? If you add a base, OH minus concentration will go up, and H plus concentration will be now lower than the OH minus concentration. So, therefore, medium will be basic. Due to the reaction above, the H3O plus concentration is equal to OH minus concentration. Therefore, the salt solution mentioned above have a neutral pH, and at 25 degrees Celsius temperature, the neutral pH is 7. So when it comes to this particular salt solution, we have a neutral pH of 7, as this equilibrium of water is not disturbed by this reaction. Examples of neutral salts. So all of these that are given over here are neutral salts, and each and every one of these salts that are mentioned here is produced through a reaction between a strong base and a strong acid. A strong base and a strong acid. So if you randomly take something like barium nitrate is, if you take a look at few examples out of the salts here. Now barium nitrate is made of barium hydroxide and nitric acid. So when these two react together, apart from forming water, the salt that is formed is barium nitrate. Barium comes from the strong base barium hydroxide, nitrate ion comes from the strong acid nitric acid. So the salt that is formed is a neutral salt. The above salts are made through strong acid, strong base reactions. So therefore, all of these salts are considered to be neutral salts. So if you pick any of these salts and dissolve it in distilled water, will there be a pH change? Would you observe a different pH other than pH 7 in the solutions that are formed? Answer would be no. When it comes to any of these salts dissolved in water, if the salt is neutral, the pH of the distilled water should not change. So we have distilled water which is at pH 7. After dissolving the salt, the resultant solution should also have a pH of 7. Salts formed through strong acid and weak bases. Very important. Strong acids and weak bases. So these are acidic salts. I also told you, if you're trying to remember how the salts are going to be acidic, basic or neutral, the easiest way is to take a look at out of the two which one is having the term strong. So acid is the one that is having the word strong, so the salt is going to be acidic. If out of the two reactants, acid is a strong reactant, the salt is going to be acidic. So some strong acids are given over here. We saw this set of strong acids earlier as well. And some weak bases are given here. We have ammonia, aqueous ammonia. We also refer to it as ammonium hydroxide here. Then we have primary, secondary and tertiary amines. So this is a primary amine that we have written here. So that is a weak base. And then we have secondary amines, right, dimethylamine. So that is going to be a secondary amine which is a weak amine. The earlier one was a primary amine which is methylamine. And then we have tertiary amines, trimethylamine, which is going to be a weak base as well. Each of these amines are weak bases. Apart from that, ammonia or ammonium hydroxide is also a weak base. Strong acid weak bases form acidic salts. So if you take a look at some strong acids along with weak bases, acidic salts are produced. HCl and ammonium hydroxide. HCl, sulfuric and nitric. What are these? These are all strong acids. Ammonium hydroxide, weak base. Ammonium hydroxide, all of these in these spaces, we have ammonium hydroxide, which is very clearly a weak base that you come across a lot in your syllabus. And students, at that point, you can see the salts that are formed. Ammonium chloride. The ammonium ion comes from a weak base. Chloride ion comes from a strong acid. So this salt that is formed is a acidic salt. We have ammonium sulfate. Ammonium is coming from a weak base. Sulfate comes from a strong acid. So this salt is a acidic salt, right? So out of the two, if one reactant happens to be stronger than the other, you can remember that that particular characteristic will be present in the salt. Now again, this is just a way of remembering. The logic behind involves an equilibrium reaction. We'll talk about that in a second. Actually, through hydrolysis of water, we will see how some salts are going to be acidic and some salts are going to be basic. So when it comes to remembering whether the salt is acidic or basic, one thing you can do is take a look at the reaction, and based on the more stronger reactant, we can say whether the salt is acidic, basic or neutral. If the stronger reactant is the acid, then the salt is going to be acidic. Here also, ammonium nitrate formed through this reaction. Acid is a strong reactant and base is weak base here. So therefore, the resultant salt is an acidic salt. The salts formed through reactions mentioned above are acidic in nature. Their solution will have a pH value lower than 7 at 25 degrees Celsius. Now we always mention that pH value should be lower in these mediums than 7 pH at 25 degrees Celsius. Why do we have to mention the temperature here? Now, the neutral pH at 25 degrees Celsius is pH 7. Now, this depends on the equilibrium of water. So we saw water turns into H3O plus and OH minus, and this has an equilibrium constant that is referred to as Kw value, and this Kw, which is also referred to as the ionic product of water. So this Kw, equilibrium constant, is going to be temperature dependent like any other equilibrium constant. So at room temperature, when you are talking about this equilibrium, in a neutral solution, you will have equal amount of H plus and OH minus due to this equilibrium. And when you are trying to find out the pH of this neutral solution, it will be 7. But when we increase the temperature or decrease the temperature, the equilibrium constant of water will change, and along with it, the pH at which the water will be neutral will also change, right? So when you increase or decrease the temperature of water, the neutral pH of water will no longer be pH 7, and that is why we insist on mentioning that the pH of water, neutral water, at 25 degrees Celsius is 7, because neutral water at, let's say, 70 degrees Celsius or 10 degrees Celsius is not necessarily exactly going to be pH 7. It is going to change, right? So because of that, students, it is important to mention the temperature here. At 25 degrees Celsius, if you take a water sample and if it is neutral, the pH is going to be 7. Examples of acidic salts. These salts are again formed through reactions between strong acids and weak bases. So we have some examples here: ammonium chloride, ammonium bromide, ammonium iodide. So all these chloride, bromide and iodide ions came from strong acids, and ammonium ions came from a weak base. So here again we can see all these ammonium ions coupled with strong acid anions. So therefore, all of these salts that are given here are acidic in nature, because all of these salts that are given here are acidic salts because these salts are formed through a reaction between a weak base and a strong acid. So we have these methyl ammonium bromide, right? Methyl ammonium iodide. All of these are again results of a weak base and a strong acid reacting together. So each of these salts are acidic salts. And we have methyl ammonium nitrate here. So basically students, methyl ammonium nitrate is given here. We have to indicate that very clearly. The name methyl ammonium nitrate is present here. Just wanted to show you how to write the name methyl ammonium space nitrate. So you can see this ion that is formed here is referred to as the methyl ammonium ion, right? Methyl ammonium ion is like this, CH3 NH3 plus. Positive charge is on nitrogen, but when you're drawing the Lewis structure of the ion, you can add square brackets and show the charge outside of the bracket. And then apart from that, we have nitrate ions. So you can see between these two ions, the salts that are formed are referred to as methyl ammonium nitrate salts. So what we have here is a methyl ammonium nitrate salt. Then we have other salts given here as well. And each of these salts are acidic salts. Reasons for ammonium chloride being acidic. You can see here ammonium chloride, if you take ammonium chloride solid and if you add ammonium chloride solid into water, you will see the pH of water or pH of the solution will be lower than pH 7. Now distilled water pH level pH value is 7 at room temperature or 25 degrees Celsius. If you take a little bit of distilled water, dissolve ammonium chloride salt in this distilled water, the resultant solution will have a pH value lower than that of pH 7. Ammonium chloride completely dissociates in water. Now ammonium chloride is a salt that completely dissociates in water. So when you're writing these dissociation reactions for a salt, most of these salts, they are fully dissociating in water. Ammonium chloride is soluble in water, so therefore it fully dissociates into ammonium 1 plus and chloride 1 minus ions. The chloride ions will not undergo hydrolysis as these ions come from strong acids. The ammonium ions coming from weak base will undergo hydrolysis as indicated below. So I will show that reaction in a second. This reaction that we need to take a look at. So in this salt, this ammonium ion that is coming into the medium came into the salt through a weak base, and the chloride ion came into the medium through a strong acid. The ammonium ions coming from the weak base will undergo hydrolysis as indicated below. So as I mentioned earlier, ammonium ions are not just going to get hydrated, they can also undergo a reaction with water. Ammonium ions are coming from a weak base. These cations are coming from weak base, and this is an ion. Chloride ion came from a strong acid. Now when it comes to any ions coming from a strong acid or strong base, will not undergo any hydrolysis reactions. But ions coming from weak bases or strong or weak acids or weak bases, they actually can undergo hydrolysis reactions. Strong acid, strong base ions will not undergo hydrolysis reactions, but weak base or weak acid ions can undergo hydrolysis reactions in aqueous medium. So this particular ion comes from a weak base, so therefore it can undergo a hydrolysis reaction. So let's take a look at this. So over here we have ammonium ions reacting with water, forming ammonium hydroxide and H+. So this is one form of the equilibrium. So we can write the equilibrium in this particular manner. Right? We have ammonium ions in the aqueous media reacting with water to form a weak base, ammonium hydroxide, right? NH4OH in aqueous media and H+. So this clearly shows H+ is now coming into the medium through this reaction. So when the H+ ion concentration in the medium will increase, this will cause the medium to be acidic. Right? H plus ion concentration increases according to this, because this reaction is happening, or equilibrium position is more towards the right hand side. Right? So therefore H plus ion concentration is higher. Or else the same equilibrium can be written in a different form as well. Now ammonium hydroxide can be written as aqueous ammonia, right? So you can write the same equilibrium in this following format. Ammonium ions reacting with water will form aqueous ammonia, which is equivalent to ammonium hydroxide. So ammonium ions reacting with water forms aqueous ammonia. At that point, instead of writing H plus, we'll have to write H3O plus to balance the equation. Otherwise, the equation would not be balanced. So students, H3O plus and H plus are essentially the same thing, right? They are equivalent to one another. They are same thing. So this means in the medium, H plus ion concentration or H3O plus ion concentration is high. When the H3O plus ion concentration is higher than the OH minus ion concentration, medium is said to be acidic. So although we have written two different equilibriums here, these two equilibriums speak of the same reaction that is taking place, that is ammonium ions reacting with water to release H plus more into the medium, along with producing a weak base. So we produce this weak base here, ammonium hydroxide or aqueous ammonia. So you can ask me now, wouldn't they release OH minus? Any base will release OH minus into the aqueous medium. Wouldn't they release OH minus into the aqueous medium? The answer is yes, they would. But these are weak acids, these are weak bases. Weak bases do not fully dissociate, or weak bases do not release all of their OH minuses. So therefore students, you will not see all of this ammonium hydroxide completely dissociating to release their OH minus. Out of all of the base that is formed, only a few will release OH minuses. So therefore, they will not increase the OH minus ion concentration significantly in water. Compared to that, the H plus ion concentration has significantly been increased already. Right? So because of that students, this reaction or the base that is produced will not contribute towards making the solution basic. Instead, there's only a net increase of H plus ions. There's only a net increase of H plus ions, causing the solution to be acidic. The ammonium hydroxide formed through the hydrolysis is a weak base and would not undergo complete dissociation to release OH minus again, as I mentioned earlier. As a result, the solution will become acidic as H plus ion concentration increases due to the H plus ion formed in this reaction. So due to the H plus ions that are formed in this reaction, when the H plus ion concentration increases, acidity increases. In this case, if you consider water's equilibrium, now water's equilibrium, it always has to maintain this Kw value. So Kw value at room temperature or 25 degrees Celsius is going to be 10 to the power minus 14. Right? So Kw equation is this: H3O plus OH plus ion concentration aqueous multiplied by OH minus ion concentration. Now earlier both were the same at neutral water. Now through that previous reaction we spoke of, now H3O plus ion concentration, a new amount of H3O plus ion concentration is now introduced into the medium. Right? So earlier it was the same, but now the H3O plus ion concentration has increased. That would mean this equilibrium value is no longer going to be this 10 to the power minus 14, because why? Now if this both were x and x earlier, now we have a new amount of H3O plus coming into the medium. Now it's going to be X plus Y or some other value. So because of that, the overall Kw value should be higher than this. That doesn't make any sense because we know at a given temperature, the Kw value can't change. At a given temperature, Kw or any equilibrium constant value will not change. So how can this be happening? Actually, students, when we increase the H plus ion concentration through the previous equilibrium that we discussed, when the H plus ion concentration goes up like this, what happens is the equilibrium will be, or the reverse reaction of the equilibrium will be favored for a while. So both H plus ion and OH minus ion concentration will slightly go down. But keep in mind, earlier at neutral water, H plus as well as OH minus concentration was the same. But because H plus is additionally added into the medium, H plus ion concentration will be slightly higher. So therefore, reverse reaction will be favored. But when the reverse reaction is favored, both H plus and OH minus ion concentration come down by a similar margin. Why? Because when the reverse reaction is favored, both H plus and OH minus ions, they are reacting 1:1 ratio. Not only H plus is removed, along with that OH minus is also removed. So they both come down. Still, the H plus ion concentration will be greater than OH minus ion concentration. Initially, they are here, but after a while, they come down. But still, the H plus ion concentration is greater than OH minus ion concentration. Something to keep in mind. So when these concentrations are brought down, when the concentrations are brought down like so, at that point, these two are not going to be the same value, right? In fact, the H3O plus concentration will be greater than the OH minus ion concentration. But at that point of obtaining a new equilibrium, when you multiply their concentrations with one another, it should again end up being, when you multiply their concentrations with one another, it should again end up being the same Kw value. So equilibrium constant value would not change at a given temperature. Only thing that happens is when initial H plus concentration is increased, equilibrium position of this equilibrium will shift to the left. But even at that point, H plus concentration will be higher than OH minus concentration. But when you take their concentrations into account and when you multiply them together, you will see that the Kw value remains a constant. It comes to 10 to the power minus 14. Right? The only reason why equilibrium position shifts is to keep the Kw value a constant. Kw value doesn't change change with the temperature, is not changed. Something to keep in mind. So very important detail here. That is something you should not forget when you are dealing with this type of equilibrium here. According to Le Chatelier's principle, when the H plus ion concentration increases, the above equilibrium position will shift to the left, and at that point also we will see the H3O plus ion concentration will be greater than OH minus ion concentration. So due to this, solution will be acidic, or in other words, at 25 degrees Celsius, the pH will be lower than pH 7. Now students, we are going to see different salts and why certain salts are acidic, basic or neutral in nature. So in this case, we are going to take a look at methyl ammonium chloride being acidic. You can see methyl ammonium chloride contains this cation. This cation is coming from a weak base, and the anion Cl minus is coming from a strong acid. So over here, due to the presence of this cation coming from a weak base, this cation can undergo a hydrolysis reaction and turn this solution acidic. So let's take a look at that here. So if you take a look at this salt, it can completely dissociate in water to produce methyl ammonium ion and chloride ion separately. The chloride ions will not undergo hydrolysis as it is coming from a strong acid. However, the methyl ammonium ions coming from the weak base will undergo hydrolysis. Now we saw chloride ions will not undergo hydrolysis, but the methylammonium ions coming from the weak base will undergo hydrolysis. So the reaction is given here. We have methylammonium ions reacting with water to form methylamine and H3O plus. So since there is H3O plus introduced into the medium, now medium will have a high H3O plus concentration compared to H minus. So the medium will be acidic. When it comes to the methylamine formed through this hydrolysis, methylamine formed is a weak base. As you know, weak bases do not release a lot of OH minuses into the medium, right? So weak bases don't react with water completely here, are releasing all of the OH minuses. Instead, there's only going to be a very small amount of OH minuses coming into the medium through weak bases. So in this reaction, there's only going to be an overall increase of H3O plus ions. So therefore, we can say the medium is going to be acidic as there's a net increase of H3O plus ions. And as I have explained earlier in the previous part, when the H3O plus ion concentration increases, the equilibrium in water will shift more towards the left, right? However, even when this equilibrium shifts, there's going to be a high amount of H3O plus than OH minus. So there's always going to be, in this situation, since we have additionally added H3O plus into the medium through the previous equilibrium that I showed you earlier, through this equilibrium we can see additional amount of H3O plus is coming into the medium. Because of that, the H3O plus concentration will be higher than the OH minus. And just to keep the Kw value of the water a constant, equilibrium position will slightly shift to the left. Even after that, still H3O plus concentration will be higher than the OH minus concentration. So therefore, pH of the solution will be smaller than pH 7 at 25 degrees Celsius, meaning the solution will be acidic. Now we can move on to salts formed through strong bases and weak acids. Strong bases and weak acids. So these are weak acids: HF, HNO2, H3PO2, H3PO3, H3PO4, right? All of these organic acids that are given over here are weak acids: HCN, H2S, and then H2CO3, oxalic acids. All of these acids that are given here are weak acids. So I want you to remember these acids, because when we are dealing with different types of salts, in order to identify whether the anions that are seen there are coming from a strong acid or a weak acid, you will need to know what weak acids are. So these are a list of weak acids that we have over here, and strong bases are these. We already know them because we have studied them earlier as well. Right, so then we move on to some examples. You can see ethanoic acid, or commonly referred to as acetic acid, reacting with lithium hydroxide, and you form lithium acetate or lithium ethanoate. And this salt is a basic salt. This salt is a basic salt. As you can see, the anion, the ethanoate anion, is coming from a weak acid, and lithium comes from lithium hydroxide, which is a strong base. So this is a reaction between a strong base and a weak acid. So in this case, the salt produced is going to be basic, as the stronger reactant is the base. And over here also HCN and KOH. HCN is a weak acid, KOH is a strong base. So HCN, HF, formic acid, all of these, or methanoic acid, all of these are weak acids. KOH, LiOH or NOH, these are all strong bases. Potassium hydroxide, lithium hydroxide and sodium hydroxide, strong bases. And they are salts. Potassium cyanide is a basic salt. Lithium fluoride is a basic salt, and sodium methanoate is also a basic salt. So these are some examples of basic salt, students. So now let's analyze why lithium ethanoate is going to be a basic salt. So if you take a look at CH3COO, Li, lithium ethanoate. If you add the solid salt into water, it will dissolve in water and will fully dissociate into ethanoate anion and lithium ions. Ethanoate anion is also commonly referred to as acetate anion, something to keep in mind. And the lithium ion comes from a strong base, therefore will not undergo hydrolysis in water, but ethanoate anion is coming from a weak acid. So therefore it will undergo hydrolysis in water. As you know, weak acid anions or weak base cations are going to undergo hydrolysis reactions in water. So if you take a look at hydrolysis in water, you can see this ethanoate anion reacts with water to form its weak acid, right? So this anion or weak acid anion will react with water to form its weak acid. We saw earlier, when it comes to weak base cations, when they reacted with water, they form the weak base, right? Here, weak acid anions, when reacting with water, they will form their weak acid. Along with that, they will also produce OH minus, because we are now reacting with water. So water breaks and it will give an H plus to the weak acid anion, and OH minus ions will be separate. So this OH minus ions that are coming into the medium will increase the OH minus ion concentration in the medium, and the H3O plus concentration will be lower compared to OH minus ion concentration now. So therefore, at that point, the medium is going to be basic. The product formed here is a weak acid, ethanoic acid, and therefore it will not fully dissociate in water, releasing H plus into the medium. So this is a weak acid. There is H plus here, but this H plus is not fully coming into the medium. This is a weak base with a very small dissociation constant. So therefore, students, it will not release all of the H pluses into the medium, just like the weak base didn't release all the OH minuses into the medium. In this case, this H plus is not necessarily fully released into the medium. So therefore, in this equilibrium, there's only going to be an overall increase of OH minus ions and not H plus ions. So therefore, students, the medium will be basic in nature. So due to this reason, there will be a net increase in OH minus concentration in the medium, which would result in making the medium basic. The pH of the medium will be higher than pH 7 at 25 degrees Celsius. Due to the OH minus ion concentration coming into the medium, equilibrium position of water will change in the below manner. You can see again now OH minus ion concentration is the one that is higher, but still because of that, the equilibrium position of water will shift to the left to keep the Kw value constant. So as it happens, now we are starting from a point where OH minus ion concentration is higher than H plus ion concentration, but as they find a new equilibrium position, their concentrations will equally decrease, right? But still, the OH minus ion concentration will be higher than the H plus ion concentration. So there's going to be a basic solution formed because OH minus ion concentration is greater than the H plus or H3O plus ion concentration. So we can say the solution has a pH value greater than pH 7. And then we move on to lithium fluoride. Now lithium fluoride is also basic salt. Why is this salt basic? So lithium fluoride in aqueous medium will fully dissociate to lithium 1 plus and fluoride ions. Now when you're writing this salt, aqueous salt breaking into ions, you use this arrow without using the reversible arrow. So this arrow that is drawn into one direction is what you should draw. It's a unidirectional arrow. So when you write this equation, don't write any other arrow here. If you show that this is reversible, at that point the equation that you have written is wrong. So this fully dissociates into lithium and fluoride ions. As you have seen in the previous instances, lithium ion comes from a strong base, so therefore will not undergo hydrolysis. fluoride ion comes from hydrogen fluoride, which is a weak acid. So this anion can undergo hydrolysis in water. So therefore, students, this reaction takes place. So this is a weak acid anion, it will form its weak acid, which is HF. Along with that, since water is being hydrolyzed here, you will see OH minus will be formed. Since this is a hydrolysis reaction, or otherwise known as a water breaking reaction, you can see H is given to F minus, forming hydrogen fluoride, and we have OH minus coming from water present here as hydroxide ions. So therefore, students, there is going to be a net increase of hydroxide ions in the medium. Apart from that, this HF formed is a weak acid, so therefore the amount of H pluses that are coming into the medium is minuscule from this weak acid. So therefore, through this equilibrium, there's only going to be an overall increase of OH minus ions in the medium. Yes, HF will also increase in the medium, HF concentration will be higher, but that will not be affecting our pH that much, because the H plus coming from HF is going to be very, very minimal. So therefore, students, there's a overall increased OH minus ion concentration in the medium, causing the medium to have a pH greater than the neutral pH of pH 7. Now, again, like I said earlier, when the OH minus ion concentration increases, the equilibrium will shift to the left. So when that happens and the equilibrium shifts to the left, the H plus as well as the OH minus concentration slightly decrease, but still OH minus ion concentration will be greater than the H plus ion concentration here. So therefore, medium will have a higher pH value than pH 7. Now we move on to salts formed through weak bases and weak acids. Salts formed through weak bases and weak acids. So let's take a look at that. So over here we have a weak acid and a weak base. When they react, they form a salt, ammonium ethanoate, right? Ammonium ethanoate, or instead some of you would refer to it as ammonium acetate. So this salt completely dissociates in water to form the acetate anion and the ammonium cation or ammonium positively charged ion. Both of these ions are coming from weak reactants. Basically, acetate ion comes from weak acid, acetic acid, and ammonium ions come from a weak base, ammonia or ammonium hydroxide. These ions undergo hydrolysis reactions because both of them are stemming from either a weak acid or a weak base. So therefore, they will undergo hydrolysis reactions in aqueous medium. So when the salt is undergoing hydrolysis reactions, you will see there's going to be a weak acid reformed as well as weak base formed again. So both the anions corresponding weak acid as well as the cations corresponding weak base will be formed. And these formed acids and bases can undergo partial dissociation in water. Now these are weak acids and weak bases. They don't fully dissociate in water. They undergo only partial dissociation in water. And their partial dissociation would depend on that particular acid's acid dissociation constant and the base's base dissociation constant, right? So keep that in mind. So weak acid can undergo dissociation like so, and the weak base can undergo dissociation like this. And the equilibrium arrow should be included here, right? These are weak acids and weak bases, so they don't fully dissociate, right? There is a equilibrium developed here. Now students, how much H plus ions coming through this reaction as well as how much OH minus coming through this reaction will depend on the equilibrium constants. So if you take a look at weak acid, if the weak acid equilibrium constant is a really high value, that means the H plus ion coming into the medium is high. If the weak base equilibrium constant Kb is a small value, that means OH minus ion coming into the medium is not that high. Only a small amount will come into the medium. So you can see, compared to the OH minuses that are coming into the medium, H pluses coming into the medium will be greater. Now because of that, there is an overall increase of H plus ions in the medium. So therefore the medium will be acidic. So I'm just trying to explain to you, even when it comes to weak acid and weak base salts, whether the medium is acidic or basic depends on the weak acid and the weak base that they reform here. Now when the salt is reacted with water due to the hydrolysis reaction, the anion reforms its weak acid, the cation reforms its weak base, and based on the dissociation constants we can figure out how many H pluses and how many OH minuses are coming into the medium. If the Ka, acid dissociation constant, is greater than Kb, at that point the medium is going to be acidic. If the Ka value and the Kb value are equal to one another, at that point the solution is going to be neutral. Why? Because although H plus is coming into the medium, equal number of OH minus is also coming into the medium, because imagine the Ka and Kb for these two equilibriums are exactly the same number of H plus as well as same number of OH minus are coming into the medium, so there's no net increase of OH minus or H plus. At that point what happens? The medium becomes neutral. So in this particular case, that is exactly what happens. When it comes to ammonium hydroxide and when it comes to acetic acid, their dissociation constants, right, Ka value for the acid and Kb value for the base happens to be very similar to one another. So therefore, if you take this ammonium acetate salt, its pH is going to be neutral. In a salt formed through reaction between a weak acid and a weak base, the acidity or the basicity of the salt will depend on the relative strength of the acid and the base. If the acid dissociation constant is Ka and the base dissociation constant is Kb, then there are three different things that can happen. If the Ka is greater than Kb, at that point the salt is acidic. I explained this earlier. If Ka value is smaller than Kb, that means Kb base dissociation constant is greater. That means base will dissociate more and will release more OH minuses into the medium than the acid dissociating to form H plus ions. So therefore there is an overall increase of OH minus, making this entire medium basic. If both of these are the same, salt is neutral. In the example provided earlier, in this particular example, the Ka value for the acid that is reformed and the Kb value for the base that is reformed. So in other words, acetic acid's Ka value and ammonia's Kb value happens to be the same, right? The acid dissociation constant Ka and the base dissociation constant is Kb, and both of these values happen to be the same. So the salt form above is going to be neutral. That means we are at this particular situation 3, Ka equals Kb, so the salt that is formed is neutral. So in this particular example, the acid dissociation or Ka and Kb happens to be the same, so therefore the solution is going to be having a neutral pH. So pH is going to be 7. Now we are going to take a look at some important details here. After discussing the few different ways in which salts can be acidic, basic or neutral, we come to a more general detail here. hydrolysis of salts and their pH values. So let's take a look at the detail. When salts dissolve in water, their ions exist as hydrated ions in aqueous medium. Some may show hydrolysis reactions with water. Now first the ions get hydrated, right? And then they can further undergo hydrolysis reaction, right? Due to these hydrolysis reactions, anions or cations will form their respective acid or weak bases, actually respective weak acid or weak bases. Now we saw this earlier, right? Acetate ion, when it undergoes hydrolysis, formed acetic acid. Ammonium ion, when it underwent hydrolysis, formed ammonia or ammonium hydroxide. So these are the weak bases that ammonium ions can form, and acetate anion formed its weak acid, acetic acid. Especially when P block and D block cations, get hydrated and then undergo hydrolysis, they release H plus ions into the medium. So this is another very important detail. P block and D block cations, when they undergo hydrolysis reactions, they will release H plus ions into the medium. Due to this, H plus ion concentration will increase and will cause the solution to be acidic. The pH of the solution will drop below 7. So at 25 degrees Celsius, the neutral pH is 7. It will go below 7 when we have a P block cation or a D block cation in the aqueous medium. So if you take aluminium chloride, now chloride ions come from a strong acid, but this aluminium comes from, it's a P block cation. So we just learned P block cations will cause the release of H plus ions when they are undergoing hydrolysis reactions. So this solution is going to be acidic. Now here again we have ferric chloride. The chloride ions come from a strong acid, so therefore they do not undergo hydrolysis. But Fe comes from the D block. It's a D block cation. We learned D block cations will undergo hydrolysis reactions releasing H pluses. So this is going to be an acidic medium, so pH will drop below 7. Zinc sulfate, again zinc is a D block cation, sulfate is coming from a strong acid. So only thing that is undergoing hydrolysis is zinc, and we know D block cations, when they undergo hydrolysis, they release H pluses according to this text that we have read just now. So we can see when H pluses come into the medium, pH will drop below 7, causing the medium to be acidic. So you can see reasons for aluminium chloride. We are taking a look at some examples here. Reasons for aluminium chloride to be acidic in nature. So if you take the aluminium chloride salt, it will dissociate to form aluminium ions and chloride ions, aluminium 3 plus ions and chloride ions. So this dissociation is a complete dissociation, so the arrow should be just a single arrow, not this equilibrium arrow. And in aqueous medium, aluminium 3 plus will undergo hydrolysis to form the below equilibrium. So we know P block cations and D block cations will undergo hydrolysis reactions. So we have the hydrated form of aluminium. Now aluminium cation can form a complex like so, a hexa aqua complex. So this can undergo a hydrolysis reaction. So one of the water ligands that is attached can undergo what is known as a deprotonation. In the water molecule there are 2 hydrogens, one hydrogen can be removed. So this is referred to as a deprotonation. So also overall this can be considered a hydrolysis reaction. So due to this, you can see you have now one water molecule losing one of the hydrogens and forming an H plus here, and you can see there were 6 water molecules here. Now since one water molecule lost a hydrogen, it is present as a OH minus ion. Overall charge of the complex is now +2. So because of this, there will be a small amount of H plus ions that is additionally coming into the medium, causing the H plus ion concentration to elevate compared to the OH minus ion concentration. So therefore, now the medium is going to be acidic. This reaction will release H plus ions into the medium. Due to this, H plus ion concentration will increase and will cause the solution to be acidic. The pH of the solution will drop below 7. The salts that are formed with aluminium 3 plus ions, which is a P block cation, along with anions of strong acids, are acidic. So anions of strong acids are given here. All of these aluminium salts that are formed along with these strong acid anions happen to be acidic. Why? Aluminium, which is a P block cation, can undergo hydrolysis reactions and will form H plus ions while they develop an equilibrium. So due to the production of, or due to the formation of this H plus ions through hydrolysis reactions, the medium will become acidic. So you can see aluminium sulfate, aluminium nitrate, aluminium perchlorate, aluminium iodate, AlI3. So if you take something like AlI3, what happens is, now we know iodine, now AlI3 can undergo complete dissociation to form aluminium 3 plus aqueous ions and 3 iodide ions. These are all aqueous. You can write the resultant iodide ion comes from a strong acid, so therefore it is not going to undergo any hydrolysis reactions. However, the aluminium ion, Al3 plus ions, is a P block cation. It can undergo hydrolysis. Actually, aluminium 3 plus ions are present in the aqueous medium as AlH2O6 3 plus, and we can show the equilibrium reaction that is taking place. Al OH H2O 5 2 minus or 2 plus, sorry, right, earlier it was 3 plus, now it is 2 plus. Apart from that, we can see the formation of a H plus as well. So this H plus that is formed or that is released into the medium through this equilibrium is a reason why we have acidic nature in these salts, right students? So in each of these salts, the aluminium ions that are released will undergo hydrolysis reactions as indicated here, and will release H plus ions into the medium, causing the medium to be acidic. Now, reasons behind salts with D block cations being acidic. So normally students, we do have now D block elements starting from scandium, vanadium, titanium, but their salts are not very commonly used in the lab. We normally start talking about different types of salts in the lab that are coming after chromium, including chromium salts, manganese, iron, cobalt, nickel, copper, zinc. These salts are more commonly available in the lab, so that's why we have these salts listed here. So salts that are stated above are acidic in nature. They are acidic in nature, and the reason is each of these salts, if you observe, they are accompanied by a anion that is coming from a strong acid like these, but the cation is a D block cation. Now D block cations do undergo hydrolysis reactions, just like we saw with aluminium. Aluminium was a P block cation, but similarly D block cations will also undergo hydrolysis reactions. So they first actually get hydrated, right? So if you read here, strong acid anions do not undergo hydrolysis. However, the D block cations will first get hydrated and then will undergo hydrolysis reactions in aqueous medium. This will release H plus ions into the medium, and due to this H plus ion concentration will increase and will cause the solution to be acidic. So students, that is what is taking place here in this example as well. We have ferric chloride, which is containing a D block cation as well as an anion coming from a strong acid. And if you take this salt solution, we know the ions are fully dissociated like this, right? And this strong acid anion is not going to be undergoing any hydrolysis reactions. However, the D block cation, it will undergo hydrolysis reaction. So first, the cation is going to get hydrated. It actually forms a complex with 6 water molecules, right? So hexaquion 3 complex. Now, actually, due to this small nature of these D block cations and the large charge on these D block cations, what happens is, students, they have like a bit of a higher charge density, and the water ligands that are bonded to it is pulled very strongly towards it, right? This will cause some water molecules to undergo what is known as a deprotonation. It's actually breaking of the water molecule that happens, right? So therefore it can be classified as a hydrolysis reaction, also referred to as a deprotonation reaction. So in this case, you can see when these water molecules are very strongly attracted towards the Fe cation, it can make some water molecules lose their hydrogens and will form H plus ions, right? So electrons are attracted more towards the oxygen atom when they are attracted more towards the Fe3 plus cation. So the oxygen hydrogen bond weakens and hydrogen can get removed from the water molecule. So this H plus will be removed, right? And then you can see the water molecule has undergone a hydrolysis or deprotonation, and it is forming OH minus ions here. So you have formed this hydrated form of the D block cation, and now one water molecule has undergone hydrolysis, and you can see one H plus is removed. And this can happen again, removing another H plus ion. This will release H plus ions into the medium. Due to this, H plus ion concentration will increase and will cause the solution to be acidic. So ferric ion solutions especially are having very observable acidic nature. So that is because of this particular reaction. Zinc, and in this case, if you take zinc perchlorate, you can see actually what we wanted to write here was zinc chloride, right? So we'll write zinc chloride here. Right? Zinc chloride, it will undergo dissociation to form zinc 2 plus along with 2 Cl minuses. We can talk about zinc perchlorate as well. Perchlorate ion also is coming from strong acids, so even that example would have been correct, but the equation that was written here was wrong. So zinc chloride will form zinc 2 plus and chloride ions. Chloride ions are coming from a strong acid, so therefore it is not going to undergo hydrolysis, but zinc 2 plus ions can undergo hydrolysis as indicated below, and this can release an H plus. This will release H plus ions into the medium. Due to this, medium will be acidic. Now students, after talking about the theory parts, we are now going to move on to our experiment that we are going to conduct in a while. So we have this equipment that we need, right? Test tubes, measuring cylinders, balance, white paper, these are needed. We use these chemicals. These are different salts that we'll be using. So we'll be taking a look at all these salts in the next coming slides. So over here, we have the method. So we are going to weigh approximately 0.5 grams of each salt and put them into a clean test tube separately. And then we are going to prepare aqueous solutions of each salt by dissolving 10 cubic centimeters of distilled water. Right, we take test tube, we add about approximately 0.5 grams, and then we add water to dissolve them. Right, we add about approximately 10 cubic centimeters of water. And add 10 cubic centimeters of water to separate test tube. Add 2 drops of universal indicator or a piece of pH paper into each of the test tubes. So you can test the pH of each solution with the use of a pH paper. So we have a pH chart coming along with the pH paper. So you can take a pH paper and you can test the pH with the use of pH paper, or else we can use the universal indicator solution. Keep a white paper behind the test tube in order to observe the colors properly. Determine the approximate pH value. So the word very approximately is very important. So determine the approximate pH value of each solution by comparing with relative color code. So with the universal indicator bottle as well as the pH paper, you usually get color charts. So when you use the universal indicator as guided in the instructions, you will see when you add a few drops of universal indicator to any of these solutions, based on their pH, the solution will change color. And then you can compare that color against the color chart that is given to us. So then we can identify the approximate pH. The approximate pH, not the exact pH. Approximate pH can be identified with the use of this comparison. Observe that dissolving some salts change the pH of distilled water by referring to the test tube containing the sample of distilled water. Now earlier we took one test tube and just add some distilled water here. So we can add universal indicator to that and see the pH. Right. So when you are taking other solutions, you will see they will change color compared to the color that is seen in the distilled water that is added with universal indicator. Complete the following table. So we'll take a look at what we are dealing with. So here, students, we have some results. So let's take a look at aluminium, ammonium chloride, zinc chloride, magnesium sulfate, and water, and sodium chloride. So if you take a look at these, you will see if you take a small solution of aluminium chloride and if you add a universal indicator, it will turn into a bit of a red color. Even pH paper will turn into a red color. So if you compare it against the color chart, you will see this particular red color is matching along with the pH 3 color in the color chart. So that means the aluminium chloride solution has approximate pH of pH 3 and ammonium chloride has approximate pH of around pH 5. These are all acidic pHs all the way up to magnesium sulfate, right? So why? Because over here we can see aluminium ions, which is a p block cation. So therefore, as they hydrolyze in water, they release H pluses into the medium, making the medium acidic. So that is why we have an acidic pH here. When it comes to ammonium chloride, ammonium ions are coming from a weak base ammonia, and chloride ions are coming from a strong acid. So since this particular salt is formed between a strong acid and a weak base, the weak base anion can undergo hydrolysis in aqueous medium and release H pluses, causing the medium to be acidic. Or else you can use this easy non-logical method to remember or just to figure out whether it's going to be acidic or basic. I told you, if you can figure out what are the acid and the base that is reacting to produce this salt, based on the more stronger reactant, we can determine whether the salt is acidic or basic. So ammonium ions come from ammonia or ammonium hydroxide, which is a weak base. HCl gives this Cl minus ion. So HCl is a strong acid. So strong acid weak base reaction. So acid is the one that is strong. So the salt that is formed is acidic. Here also we have zinc 2 plus ion, which is going to hydrolyze or undergo hydrolysis reaction in water, release H plus. So the medium is acidic. Magnesium sulfate, sulfate comes from sulfuric acid, strong acid, and magnesium ions come from magnesium hydroxide, which is not considered a strong base. So therefore, the pH of the solution happens to be acidic. Water and sodium chloride. Now, sodium chloride is neutral salt, so pH is 7. Water is neutral, so therefore pH is 7. And then again we can see ammonium acetate. It is also neutral. We saw earlier. This salt is a product of weak acid, weak base reaction. However, the weak acid and the weak base that is involved here has the same dissociation constant values. Ka value is equal to Kb value. So their dissociation constant values are the same. So because of that, it happens to be neutral. And here, weak acid, strong base, we have basic pH. H2S, which is weak acid, sodium hydroxide, strong base, produces this salt. So therefore, strong base, weak acid, strong base sodium hydroxide, weak acid H2S produces a basic salt. And lastly, we have sodium carbonate, which is a basic salt, stems from sodium hydroxide and carbonic acid H2CO3, which is a weak acid. So strong as base, weak acid, strong base, weak acid produces a basic salt. So you can now actually, without the predictions, you can just use the universal indicator and the color chart to approximately determine the pH. That's what we have done here. So how do we do this in the lab? We can add about 5 grams of aluminum chloride crystals or solid into the test tube, add about 10 cubic centimeters of water, and add about 3 drops of universal indicator. Right? When you add about 3 drops of universal indicator, what happens? You will see a color. In this case, we have a bit of a red or color close to red. So then you get the universal indicator color chart. So you place it next to it, right? And then try to observe with what color it matches. So then you will realize, okay, this color in this test tube matches with this particular red color, and then you can read the pH right next to it. And the pH happens to be, in this case, around 3. Through these observations, we can conclude the solution is acidic. Yes, pH 3 is a small pH value, so therefore it's a smaller value than pH 7, so therefore all of these are acidic. So I will write over here, any pH that is towards the left is acidic. pH 7 is neutral, any pH towards the right is basic. Right. So then we have ammonium chloride. We do the same thing, students, over and over again. We take 5 grams of 0.5 grams of ammonium chloride crystals, add the universal indicator and water, and then you will see a color. And then you try to match that color with this color chart, right? So you can see a yellow color is observed in pH 5. So therefore this solution is completely acidic. pH 5 is acidic pH, and you can see the yellow color corresponds with the yellow color in the pH color chart. And the same thing can be said about zinc chloride as well. Zinc chloride will also provide us with a yellow color when added with the universal indicator. So that is also an acidic solution. Magnesium sulfate gives us a slight green color. So let's take a look at where this slight green color appears, right? So you can see after yellow, what you see is a slight green color. So that green color indicates the solution's pH is 6. So when it comes to magnesium sulfate solution, the pH is 6. And the distilled water, of course, it aligns perfectly with the neutral pH, which is pH 7. And if you arrange them in the increasing order of pH, you can see aluminum chloride was pH 3, ammonium chloride was pH 5, and magnesium sulfate was pH 6. And now water is pH 7. So this is the ascending order of the pH values of different solutions. And over here also we have sodium chloride. It's a neutral salt, so the pH happens to be 7. So in the pattern that we saw earlier, after water now we have sodium chloride, but both of these will have the same pH value. Here also we have ammonium acetate. So ammonium acetate salt we identified earlier is a neutral salt, and we explained why that is a neutral salt. Ka of acetic acid and Kb of ammonium hydroxide happens to be the same value. So therefore either acid or the base is not going to be stronger than the other, so which results in the formation of a neutral salt. So the pH of the solution in the increasing order, when you write it like that, you can see aluminium chloride, ammonium chloride, magnesium sulfate, and then from water all the way to ammonium acetate. All of the solution, water, sodium chloride and ammonium acetate, are the same pH, which is pH 7, neutral pH. Even sodium acetate, when it comes to sodium acetate, we have a weak acid coupled with a strong base cation, weak acid anion and a strong base cation. So the medium is going to be basic, right? You can see a bit of a darker green color which corresponds with pH 9 from the color chart. So this is a basic salt, right? And we do know based on the pH to communicate whether it's a basic, acidic or neutral salt. So if it is pH 7, it's neutral. If it is less than pH 7 in 25 degrees Celsius temperature, if a solution has a pH value less than 7, they are acidic. If a solution's pH is greater than pH 7 at 25 degrees Celsius, it is basic. Determine the pH of sodium sulfide solution. The same steps will be used, and after adding the universal indicator, you can see we have a bit of a very dark green color which corresponds to a pH of 10, and you can see the ascending order of pH of different solutions, and pH is going to be highest in this case in sodium sulfide, even more basic than sodium acetate. And finally we have sodium carbonate. Now sodium carbonate again is a bit of a basic solution. You can see this particular color that you see over here. If you compare it against the color chart, it reads pH 12. It's a bit of a really high pH value. So that means the sodium carbonate solution that we have over here is a basic solution. Now students, here we move on to a bit of a summary of this theory part that we have covered. So here we are looking at the different types of acids and bases that react and the nature of the salt that is produced. So, and we have some examples here as well. So for example, when a strong acid and strong base reacts, the salt that is produced was neutral, and some examples are given here: sodium chloride, potassium sulfate, calcium nitrate, barium chloride. These are all neutral salts. When the acid is strong and the base is weak, when the acid is strong, base is weak, out of the two reactants, the strong reactant is the acid. So therefore we can say the salt is acidic. This is just an easier method of remembering. So the salt is going to be acidic since the acid is the one that is strong. And at that point, what is actually happening is, students, if you take the look at these examples, you can see the chloride ions that are coming from the strong acid is not going to hydrolyze in water, but the cation, ammonium ions, are coming from weak base, and these ions are undergoing hydrolysis in water, releasing H pluses. That is why the medium is going to be acidic. So ammonium chloride, ammonium nitrate, ammonium sulfate, methyl ammonium chloride, these are all going to be acidic salts. If the acid is weak and the base is strong, at that point the salt is basic. The stronger reactant is base, so therefore salt is going to be basic. We can say sodium acetate, or sodium cyanide, potassium phosphate, barium acetate. All of these are as a basic salts. All of these are basic salts. We can see these anions that you see over here. All of these anions that you see over here are coming from weak acids. Acetic acid, cyanide, hydrogen cyanide, and phosphoric acid. Acetic acid is a weak acid, hydrogen cyanide is a weak acid, and phosphoric acid is also weak acid. If you have both weak acid and a weak base, we can't always say that it is going to be neutral, but in this particular example that we have given, it is a neutral salt. Now when it comes to weak acid and a weak base, whether the salt is going to be actually neutral or acidic or basic will depend on their Ka values and Kb values. Weak acids will have a Ka value, weak base will have a Kb value. So based on the Ka and Kb value, we can comment on their relative strength. If the Ka value happens to be slightly greater than the Kb value, then we can say, although they are weak acid, the weak acid happens to be slightly more stronger than the weak base. So then what happens? The produced salt is going to have acidic properties, right? So it's going to be an acidic salt. If the Kb value is slightly higher than the Ka value, then the base is relatively stronger than the weak acid, right? The weak base happens to be relatively stronger than the weak acid, causing the formed salt here to be basic. If the Ka and the Kb happens to be the same, if they have the same magnitude, at that point, like in this case, their Ka and Kb values are the same. So therefore, at that point, the formed salt is going to be neutral. Right, so we'll take a look at one more example here on how to fill a table like this. So predict whether the salts given below are acidic, basic or neutral. So we have lithium fluoride. Now lithium fluoride, students, we'll start with that. Lithium is coming from a strong base, fluoride and comes from a weak acid. So therefore, it's a basic salt, lithium fluoride. Lithium ions come from strong base, lithium hydroxide. Fluoride comes from a weak acid, HF, hydrogen fluoride. So therefore, it's a reaction between a weak acid and a strong base. So therefore, this is going to be a basic salt. We have sodium nitrate. Both come from strong acid and a strong base. Sodium comes from sodium hydroxide. Nitrate part comes from nitric acid. So it is strong acid, strong base. The answer is neutral. So sodium nitrate, NaNO3, is a neutral salt. Potassium sulfate. Potassium comes from potassium hydroxide, which is a strong base. Sulfate comes from sulfuric acid, which is a strong acid. So what is it? It is also a neutral salt. Potassium sulfate is a neutral salt. We have barium acetate. Now barium comes from a strong acid. Barium comes from a strong base. Barium comes from a strong base, barium hydroxide. And the anion here is acetate or ethanoate. Ethanoate anion comes from ethanoic acid, or commonly referred to as acetic acid, which is a weak acid. So this is formed through a reaction between a weak acid and a strong base. The cation over here does not undergo hydrolysis. However, this weak acid anion can undergo hydrolysis in water and release OH minus. So this is going to be a basic salt. Since the reaction since this barium came from a strong base and the anion came from a weak acid, we can predict that this salt is going to be a basic salt. So this is going to be basic. You have to be able to not only predict but also explain why it is going to be basic. You have to say this is a cation coming from a strong base, so it will not undergo any hydrolysis reaction in water. but this anion comes from a weak acid. So these weak acid anions can undergo hydrolysis reactions in water. In this case, when it undergoes hydrolysis reactions in water, it releases an OH minus ion when it undergoes hydrolysis. So therefore, OH minus ion concentration in water will increase, causing the medium to be basic. And then we have ferric nitrate. The nitrate comes from a strong acid. Now Fe3 plus over here is a D block cation. Now D block cations in aqueous medium can undergo hydrolysis and release H plus ions into the medium. So therefore, this particular salt that we have here is an acidic salt, FeNO3 thrice. We can say the same about ferrous sulfate or ferric. In this case, this is ferrous sulfate. Ferrous sulfate also react the same way. It's a D block cation and sulfate ion comes from a strong acid, so therefore it is not undergoing hydrolysis, but Fe2 plus can undergo hydrolysis in aqueous medium to release H plus ions. So therefore salts are acidic. Barium bromide. So barium ions come from strong base, bromide ions come from strong acid, it's HBr. So therefore this is a neutral salt. We have cobalt chloride. Cobalt is a D block element. We know they undergo hydrolysis in aqueous medium. Chloride is coming from strong acid, so they are not hydrolyzing, but cobalt is undergoing hydrolysis reactions in aqueous medium to release H plus, so therefore this is acidic. Lithium bromide, again strong base lithium hydroxide and HBr, a strong acid, reacts to form this, so this is neutral. Strong acid, strong base reactions form neutral salts. And here also we have lithium sulfate, strong base, strong acid. So this is lithium sulfate, a neutral salt. Lithium cyanide. Lithium is coming from a strong base, but cyanide ion comes from a weak acid. So strong base, weak acids produce basic salts. So lithium cyanide is a basic salt. Sodium sulfite. Now sulfate is a strong acid, or sulfuric is a strong acid, but this sulfite ion comes from sulfurous acid, which is not a strong acid. So this is produced through a reaction between a strong base and a weak acid. So this is going to be a basic salt, Na2SO3. Sodium phosphate. Now phosphoric acid is a weak acid. Sodium hydroxide is a strong base. So strong base, weak acid reaction produces sodium phosphate. So therefore, students, this is a basic salt. Strontium chloride. Now strontium hydroxide and HCl will produce this. Both are strong. Strontium hydroxide is strong, as well as HCl is a strong acid. So therefore, this is going to be neutral. SrCl2. And we have ammonium hydrogen phosphate, right? So in this case, we have again dihydrogen phosphate, ammonium dihydrogen phosphate, and in this case again, this is an ion coming from a weak acid. Sodium comes from a strong base, so therefore this is going to be a basic salt. Sodium dihydrogen phosphate, PO4. Sodium comes from a strong base, dihydrogen phosphate is coming from a weak acid. So students, now we have discussed sodium dihydrogen phosphate. So this is basic, and when it comes to these anions also, they are stemming from weak acids, and sodium is stemming from or coming from a strong base, sodium hydroxide. So these salts are going to be obviously basic. So this is sodium hydrogen phosphite, and this is sodium hypophosphite. So both of them are going to be basic salts. These are going to be basic salts. And then potassium sulfide. So potassium sulfide is formed when potassium hydroxide, which is a strong base, reacts with H2S, which is a weak acid. So this is a salt that is produced with the reaction between weak acid and a strong base. So the resultant salt is a basic salt. So K2S is a basic salt. So this is how you can identify whether the given salt is acidic, basic or neutral. Whether the given salt is acidic, basic or neutral can be identified in the following manner. And students, when it comes to explaining why the solution ends up being acidic, basic or neutral, you have to talk about the hydrolysis reactions that are taking place. Strong acid, strong base, the ions that are formed through strong acids or strong bases usually do not undergo hydrolysis, but weak acid, weak base ions will undergo hydrolysis. Along with that, we also learned P block cations and D block cations will also undergo hydrolysis reactions after they are hydrated. So you have to keep these details in mind in order to predict whether a given solution or whether a given salt is acidic, basic or neutral. So now students, with this we can conclude the theory parts revolving around our experiment number 35. So it is time for us to now move into the lab and actually conduct this experiment and observe the color changes and observe the pH values of different solutions we come across in this experiment. So without further ado, let's move into the lab and actually conduct this experiment. GCE Advanced Level Chemistry Practical Series experiment number 35, experimental determination of acidic, basic and neutral nature of aqueous salt solutions by testing their pH. So the aim of this experiment is to take different salts and form aqueous solutions of these salts, and then with the use of a universal pH indicator, we are going to measure their pH value. And based on the pH value, we are going to categorize each of these aqueous solutions as acidic solutions, basic solutions, and neutral solutions. So the aim of this experiment is to identify the acidic, basic, or neutral nature of each of these aqueous solutions that we form here. Now let's move on to identifying the different reagents we will be using for this experiment. Students, let's take a look at the chemicals we will be using for this experiment. We'll be using sodium chloride, which is a very common substance for you, salt that you use when you are cooking. And we have sodium acetate, we have ammonium acetate, ammonium chloride, zinc chloride, aluminium chloride, and magnesium sulfate. Apart from that, we will be using universal indicator solution. We have taken a small amount of our universal indicator into this small beaker here. We will be using a dropper to take small amounts of universal indicator. We have distilled water. We will be using distilled water to make aqueous solutions of each of these compounds that we have here. Apart from that, we will be using small plastic spoons to take each of these solids into these test tubes that we have here. So we have test tubes to make our solutions. Apart from that, we'll be using a measuring cylinder to measure 10 milliliters of water when we are making each of these solutions. So these are the chemicals and the equipment we will be using for this experiment. Now students, we are going to be measuring the pH of different aqueous solutions in this experiment, and in order to do so, we are going to take approximately about 0.5 grams of each solid that we have with us, and then we are going to dissolve it in about 5 cubic centimeters of water. And to each of these aqueous salt solutions, we are going to add the same amount of universal indicator. We are going to add a few drops of universal indicator to each of these aqueous salt solutions we have with us. And we are going to make sure that we are adding same amount. We are adding the same amount of the universal indicator to each of these solutions to keep everything or all the factors constant. We are going to make sure we are adding the same amount of universal indicator to each of these aqueous solutions that we prepare. When we are getting started, one of the most important things is the color chart that is given in the back of our universal indicator bottle. As you can see here, students, we have the color chart that is given here. This color chart helps us determine the pH of a given solution. When we add a few drops of universal indicator to a solution, the solution will change color. Because of the presence of universal indicator, it will give out different colors. And based on the color that the solution is giving off, we can actually figure out the pH of that particular solution. So when it comes to observing these colors, since it is difficult for you to observe these colors that we have over here, we have scanned this label and displayed the same colors on this digital screen that we have here, so that we can very clearly observe these colors. And if you want to properly see the colors, we can move around. We can observe these colors very clearly. Now, we are going to first measure the pH of water. We are going to first measure the pH of water. In order to do that, we are going to take about 5 cubic centimeters of water. We have a measuring cylinder here. We are going to add 5 cubic centimeters of water to this measuring cylinder. And then we are going to transfer 5 cubic centimeters of water into a test tube. And then we have a small amount of universal indicator taken into a small beaker here. You can observe the universal indicator is red in color. And we are going to take a small amount of universal indicator and we are going to add a few drops of the universal indicator into our test tube here. And we are going to mix it really well. As you can see, when we added the universal indicator to water, the indicator was no longer red in color. It changed color, right? So this color will tell us the pH of water. So now let's compare it against the pH chart we have over here. We can see when you are moving all the way from pH 411 that we have here, when we are moving up, we can see the pH of this water is 7. You can see the color that you observe in this test tube is exactly pH 7. It is not pH 6, it's not pH 6.5. It clearly matches with the pH 7 according to this color chart. So students, the distilled water that we have at the lab is having a pH of pH 7. Now students, we have observed the pH of distilled water that we have in our lab. Now let's move on to our first salt. We have sodium chloride. So let's make a small aqueous solution of sodium chloride and then observe the pH of a salt solution. We have our sodium chloride here. We are going to take a very small amount of sodium chloride, approximately 0.5 grams of sodium chloride. And we are going to add this amount into a test tube. As you can see, sodium chloride is a white color solid. I'm fully aware that all of you know this by now. Then we'll measure 5 milliliters of water. And then we'll transfer this 5 milliliters of water into our sodium chloride solid that we have here. Now we have dissolved the sodium chloride that we took into our test tube here. Now we can move on to adding the same amount of universal indicator that we added to our water will be added here as well. So we are going to make sure that we add exactly the same number of drops of universal indicator into the sodium chloride aqueous solution as well. Right students, let's observe the color of this sodium chloride solution. If you pay close attention, you can see sodium chloride also is having a color that is close to pH 7. So the sodium chloride solution that we prepared had a pH of pH 7. This indicates the sodium chloride solution is a neutral solution. As you know students, when it comes to room temperature, pH 7 is characterized as a neutral pH. Any pH above the pH 7 indicates that the solution is alkaline or basic. So starting from pH 7 and upwards, 8, 9, 10, 11 indicates that the solution is basic or alkaline. When it comes to pH values below 7, from 7 to 0, it indicates these values are acidic. When you are going below pH 7, pH 6, pH 5, pH 4 and so on, pH values below the value of pH 7 indicates that the solution is acidic. So what we observed for sodium chloride solution was a pH 7. So the pH of sodium chloride was 7, indicating our sodium chloride is a neutral solution. So this is clear to us that sodium chloride had a neutral pH. Now let's move on to our next solution. Now we are moving on to sodium acetate. So we have our sodium acetate here. We are going to take a small amount of sodium acetate, dissolve it in 5 cubic centimeters of water, and then we are going to add our universal indicator and observe the color of the solution. And based on the color of the solution, we can determine the pH of the solution. And based on whether the pH is below 7 or above 7, we can determine whether this solution that we prepared is acidic, basic, or neutral. We have a spatula here. We'll take a small amount of ammonium. We'll take a small amount of sodium acetate. About 0.5 grams of sodium acetate can be taken into our test tube here. As you can see, sodium acetate is white color crystalline solid. And then we are going to add 5 cubic centimeters of water. To measure 5 cubic centimeters of water, we can use a measuring cylinder. Now we have measured 5 cubic centimeters of water. Let's add that to our sodium acetate. And let's dissolve the solid. So now we have prepared an aqueous solution of sodium acetate. It's a clear solution. And we are going to add the same amount of universal indicator that we added to both of the previous solutions. We had a little bit of water. We added a few drops of universal indicator to the water sample we took, and then we add the same amount of universal indicator to our sodium chloride sample, and we have here a different salt, sodium acetate. So we are going to add the same amount of universal indicator to this sodium acetate solution as well. Now students, as you can see, when we added our universal indicator, the color of the universal indicator was red, but now we can see the solution is green in color. So the universal indicator has changed its color. Now let's compare it against the color chart that we have here and observe the pH of this particular solution. Now students, as you go down, is it blue or is it light green or is it somewhere in between? Is it light green? Is it dark blue or is it somewhere in between? You can observe that that value is 8.5. So the pH of this solution is 8.5. So students, just to give you a very clear picture, we can see the pH of this solution is 8.5. Sodium acetate has a pH of 8.5. So when you have a pH of 8.5, what does that indicate? It indicates that this solution is basic. Any pH value above the pH of 7 is indicating that the solution is basic. Why was this solution basic? Now you might have learned about the fact that when a strong acid reacts with a weak base, the salt that is formed is going to have acidic properties. And the reverse argument of this is also true, which is when a strong base is reacted with a weak acid, the salt that is formed is going to have basic properties. So sodium acetate is going to be formed as a salt when we react acetic acid or any carboxylic acid for that matter dissociates partially in water, and therefore they are weak acids. So when acetic acid reacts with sodium hydroxide, and as we know, sodium hydroxide is a strong base, the salt that is formed is sodium acetate. Sodium acetate is going to be a basic salt because it is produced as a result of a reaction between a strong base and a weak acid. Strong base being sodium hydroxide and the weak acid being acetic acid or ethanoic acid. So the product that is formed is sodium acetate and water. So sodium acetate salt that is produced is a basic salt. That is why we observed the pH of sodium acetate solution is 8.5, which is a basic pH. Now let's move on to our next salt. Now we are going to prepare an aqueous solution of ammonium acetate. We have our ammonium acetate here. We can take a small sample of ammonium acetate into a test tube. We'll take a fresh test tube and we'll add a small amount of ammonium acetate to this test tube. And to this ammonium acetate that we have taken, we can actually add 5 milliliters of water. And before we add water, we can observe the nature of the ammonium acetate. Ammonium acetate is a white color crystalline solid which is soluble in water. While keeping that in mind, we can move on to taking 5 milliliters of water into our measuring cylinder. Now we can add the 5 milliliters of water into ammonium acetate and then mix it really well. As you can see, when you dissolve ammonium acetate in water, you produce a clear solution. And to this, we are going to be adding a few drops of our universal indicator. Keep in mind, students, we are going to be adding the same amount of universal indicator that we added to the previous test tubes as well. Now students, as you can see, the color of the solution has changed. Let's compare it against our color chart here. Is it a light green like pH 7.5 or is it a yellow like pH 6.5 or is it pH 7? So students, let's zoom in and very clearly observe the color change. So we know it's somewhere between pH 6.5 to pH 7.5, but which color is it very clearly? You can observe it is not pH 6, you can observe it is not pH 7.5, it is pH 7. So students, or it is somewhat close to pH 7 than it is to pH 7.5 or it is to pH 6.5. So this solution has a pH value closer to pH 7. So keep in mind, ammonium acetate has a pH value closer to pH 7. We can say the pH value according to what we observe here in the pH chart, the pH of this solution is pH 7. So why does ammonium acetate have a pH that is close to pH 7. Ammonium acetate has a pH close to the pH 7. This is because this particular salt can be formed between the reaction of a weak acid and a weak base. If you take ethanoic acid or acetic acid, ethanoic acid is another name for acetic acid. So if you take ethanoic acid and react it with ammonia, you will be forming ammonium acetate. So ethanoic acid is a weak acid and ammonia is a weak base. So when you react them together, the salt that is formed is going to be forming a neutral aqueous solution if both the acid and the base were equally weak. So both ethanoic acid and ammonia were equally weak. Therefore, the resultant salt was forming an aqueous solution that is having a pH of pH 7, or in other words, the resultant salt was neutral. Or in other words, an aqueous solution of the resultant salt is neutral. Now, let's move on to the next part of our experiment. Now, students, we are going to prepare a solution of zinc chloride. We have our zinc chloride solid here. We are going to take a small amount of zinc chloride into our test tube and add 5 milliliters of water to it. Let's take a small amount of zinc chloride and we are going to measure 5 milliliters of water into this measuring cylinder here. So students, observe that zinc chloride is a white color solid, and we are going to add water to this zinc chloride solid that we have here. We have 5 milliliters of water, and we are going to dissolve this zinc chloride in our water that we have here. Students, as you can see, we were able to dissolve the zinc chloride and form a clear solution here. And now we are going to add the same amount of universal indicator to this test tube as well. We have made sure to keep the amount of universal indicator that we add to each test tube a constant. So we are going to be adding the same amount of universal indicator to this test tube as well. Now students, after mixing it, we can see the solution is not a red color. The universal indicator was red, but the solution's color is different, indicating we can use this color to observe the pH of the solution. So now students, when we are observing the color, please notice what color it is. It is somewhere between this particular color range. We will zoom into that color range and let's observe, is it pH 7.5? It is a green color. It is not definitely pH 7.5. Is it pH 7? No, it is too light to be pH 7. And is it pH 6.5? So it is very close to pH 6.5. So if you are having any doubts, you can move on to pH 6 and observe whether it is close to pH 6 as well. It is closer to pH 6.5 5 than it is to pH 6. pH 6 is a bit of a brighter color than pH 6.5. So this color is a good match to the pH 6.5 color that we have here. So this particular solution has a pH of pH 6.5, which indicates that this is a slightly acidic solution. Now, let's move on to observing why that is. So students, when you take zinc chloride can be prepared by reacting zinc hydroxide with hydrochloric acid. Zinc hydroxide is not very soluble in water. It is slightly soluble in water, but it is not very soluble in water. So therefore, zinc hydroxide is not a very good electrolyte. Many of the ions that are in zinc hydroxide would not enter aqueous medium. So therefore, zinc hydroxide is not a very good or very strong base. So zinc hydroxide is a weak base. Then we react zinc hydroxide with hydrochloric acid, which is a well-known strong acid. When you react this weak base with a strong acid, the resultant salt will be acidic salt. The resultant salt is an acidic salt. So that is why we observed when it comes to a solution of zinc chloride solution was acidic in nature. So now let's move on to the next step in our experiment. Now students, we have ammonium chloride here, and let's prepare a solution of ammonium chloride. We have our ammonium chloride solid. Let's take a metal spatula and a fresh test tube and add a small amount of ammonium chloride into our test tube. And then we can add 5 milliliters of water to this test tube. Before we add 5 milliliters of water, we can observe that ammonium chloride is a white color solid. And after that observation, we can move on to adding 5 milliliters of water. We have dissolved the ammonium chloride that we took into our test tube to form a clear ammonium chloride solution. Now let's add the same amount of universal indicator that we added to each of the previous test tubes. Now let's shake this to observe the color of the solution. The solution has turned into a different color. It is not red anymore. As we can see here, the universal indicator was red in color, but now there's a slight orange hue to our solution that we have here. So let's compare the color that was given off when we added universal indicator to our ammonium chloride solution. And let's find out the pH of our ammonium chloride solution here. So of course students, this particular pH chart, we don't have to start all the way from the bottom because the colors at the bottom are blue. So since we know that this is not a blue color, we can start from somewhere around 7, pH 7. So I will zoom in on pH 7 values. Now you can see it is not pH 7. pH 7 is a green color, and pH 6.5 is a green mixed yellow color, and we have pH 6, which is a bright yellow color
But then again, we have pH 5.5, which is a very good match to this color, which is a slight orange color or light orange color. If you move on to pH 5, that is going to be a darker orange color. So we can observe that pH 5.5 is a good match for this particular color. So we now know the ammonium chloride solution that we prepared had a pH of pH 5.5. So pH 5.5 is an acidic pH. pH 5.5 is an acidic pH. So why does the pH of an ammonium chloride solution turn out to be 5.5? This is because ammonium chloride salt can be prepared when you react ammonia, which is a weak base, with a strong acid, hydrochloric acid. So when a reaction between a strong acid and a weak base produces a salt, the salt is going to have acidic properties. That is why when you have a reaction between strong acid hydrochloric and weak base ammonia, the resultant ammonium chloride salt had acidic properties. So an aqueous solution of ammonium chloride produced a acidic solution, and the pH of that particular solution that we prepared was 5.5, which is an acidic pH. Now let's move on to the next salt. Now we are going to take a look at a solution of aluminium chloride. To produce a solution of aluminium chloride, we have our aluminium chloride solid here. We can take a small amount of aluminium chloride into a test tube. And we are going to add 5 milliliters of water. So we can measure it with a measuring cylinder. And we are going to add our water to aluminium chloride here, and we are going to mix it really well. After mixing it really well, we produced a clear solution of aluminium chloride. And like in the previous steps that we have done before, we are going to add an equal amount of our universal indicator to this test tube as well. As you can see, when the universal indicator was added, the solution turned to a bit of a dark color. It is not a blue color, it is more towards the acidic side of the pH scale. So let's compare this color with our pH scale that we have here. It is definitely not a yellow color, it is more towards orange or red color. So let's observe whether it's close to pH 6. It is definitely not pH 6. Is it close to pH 5.5? It is not. Is it pH 5? It's very close to pH 5. Is it pH 4? So when you observe the color of the solution, it is quite close to this color, which is the pH 4. The pH is pH 4. Now students, when you are observing these colors, you have to make sure that you find the best fit. So this test tube, the solution in the test tube is quite close to pH 4 than pH 5. So the pH of this solution is closer to pH 4 than to pH 5. So we can say that the solution has a pH of 4, or the pH of this particular solution is 4. Now, let's discuss why that is. Again, we can see the solution that we formed is a acidic salt. As you know, aluminium chloride can be produced by a reaction between aluminium hydroxide and hydrochloric acid. Aluminium hydroxide is not a very strong base, but hydrochloric acid is a strong acid. When a strong acid reacts with a weak base, the resultant salt is going to be an acidic salt. So therefore, that is the reason why aluminium chloride is an acidic salt. Keep in mind, students, the pH of the aluminium chloride that we produced is pH 4 that we have here. So because of this, this particular aluminium chloride solution that we prepared has a very acidic pH, indicating that aluminium chloride aqueous solutions are acidic in nature. Now let's move on to our final salt. As our final salt, we have magnesium sulfate. This will be a good time to remind you of the solubilities of group 2 sulfates. What happens to the solubility of group 2 sulfate as you go down the group 2? Group 2 sulfates become less and less soluble. Magnesium sulfate is soluble, but as you go down towards barium sulfate, strontium sulfate, these are insoluble in water. So please remind yourself about these types of additional theory parts while watching these videos. Now let's take this test tube and add a small amount of magnesium sulfate. Now let's add a small amount of magnesium sulfate. As you can see here, students, magnesium sulfate is a white color crystalline solid. And to this, we are going to add 5 milliliters of water. We have taken 5 milliliters of water and we are going to add this water to our magnesium sulfate solid. Then we are going to dissolve the magnesium sulfate solid that we have taken into our test tube here. Now we have dissolved our magnesium sulfate solid here. To this, we are going to add our universal indicator, while keeping in mind that we added the same amount of universal indicator to each of these different solutions we prepared in the earlier instances. So the same amount of universal indicator is going to be added to this solution as well. Now students, we have formed a solution here, and let's observe the pH of this solution by comparing this color to our pH chart. So this pH seems to be close to pH 7. So let's zoom in to those colors. Is it pH 7.5? No. Is it pH 7? It looks like it is very clearly pH 7, but let's compare it to pH 6.5 as well. Is it pH 6.5? Is it pH 6? Certainly not. So it is very close to pH 7. It is very close to pH 7. This indicates the magnesium sulfate aqueous solution has a pH of pH 7. So students, we observed when it comes to magnesium sulfate, the pH of magnesium sulfate was 7. So therefore, it is a neutral salt, or the pH of an aqueous solution of magnesium sulfate will be neutral. Magnesium hydroxide, when reacted with sulfuric acid, can produce magnesium sulfate. So this is a reaction between a strong base and a strong acid. Therefore, the salt that is produced was also a neutral salt, or the salt that is produced will have a neutral pH. Students, as an additional reaction, we can take a small amount of strong acid such as sulfuric acid and add our universal indicator to our sulfuric acid solution and observe what the pH of sulfuric acid is. Let's take a small amount of sulfuric acid into our test tube here. And let's proceed to add a small amount of pH indicator as well. We can see upon addition of the indicator, it immediately started changing color to a very strong red color. So this is a very strong red color. So students, upon the addition of a few drops of universal indicator to our sulfuric acid, we can observe that it turns to a bright red color. That particular bright red color is nowhere to be seen in this color chart. That is because the universal indicator that we have here gives us a color chart for pH values ranging from pH 4 all the way up to pH 10, actually pH 11, all the way up to pH 11. So it goes from pH 4 all the way up to pH 11, but it does not give us the color of solutions that are formed with lower pH values like pH 3 or pH 2. So because of that, we can be very certain this particular red color is corresponding to a lower pH than pH 4. So sulfuric acid is quite a lot more acidic. pH of sulfuric acid solution that we have here is not going to be 4. It is a lower pH value than pH 4. Unfortunately, since this particular color chart does not include the color of pH values that are lower than pH 4, we can't be sure exactly what pH value this sulfuric acid is at. However, we can be certain that the pH value of sulfuric acid is lower than pH 4. Now, let's take another test tube and add a small amount of sodium hydroxide. This is concentrated sodium hydroxide, so let's dilute it a little further by adding water. We have diluted the sodium hydroxide. We have taken concentrated sodium hydroxide and now diluted it a bit further. To that, let's add a small amount of our universal indicator. As you can see, when the universal indicator is added, the color started changing immediately. And the color that is observed here is a dark purple color. So let's compare the color that we have observed here with the color chart here, and you will be noticing that this purple color that we see here is nowhere to be seen in this color chart. That is because, students, the sodium hydroxide solution is more basic than the pH values that are indicated in this particular color chart. So the highest pH value that this color chart indicates is pH 11, but the sodium hydroxide solution that we have here might have a higher pH value than pH 11. Because of that, the color that is produced here is not observed in this color chart that we have here. So now it is very clear, when there is a very strong acid, we can observe a very clear red color in our universal indicator solution, and if you have a very strong base, the color is going to be a strong blue, purple color. With that, we can now move on to our summary. Students, let's take a look at the summary of our experiment number 35. In this experiment, we wanted to observe the pH of different aqueous salt solutions. So we took small solid samples of different salts and dissolved each of these salts in 5 cubic centimeters of water to prepare their aqueous salt solutions. Afterwards, we added a few drops of universal indicator, and we made sure to add the same amount of universal indicator to each of these solutions. When we add universal indicator to a solution, the solution will change its color due to the presence of the universal indicator. So using the color that is seen in the solution after the addition of universal indicator, we can determine the pH of the solution. Usually, when you purchase a universal indicator reagent bottle, it will come with a color chart. So we have that color chart here. We compared the colors of each of the different solutions that we have here with this color chart, and then obtained the pH value of each of these solutions. We initially added a few drops of universal indicator to water. The water turned to a greenish solution. Due to the presence of universal indicator, now the water has turned to a greenish color. You can compare this color against the color chart of the universal indicator, and when we did that, we observed that the pH of water was pH 7. pH 7 is the neutral pH at this room temperature. So the water that we have has a neutral pH. Then we moved on to sodium chloride. So you can see the sodium chloride, when added with our universal indicator, turned to a greenish color. After comparing this color against our color chart, we found out the pH of sodium chloride aqueous solution is also 7, indicating that sodium chloride solutions are also neutral according to their pH. So sodium chloride aqueous solutions are neutral solutions. Then we took an aqueous solution of sodium acetate. Sodium acetate, when added with universal indicator, turned to a darker green color. And when we compared this dark green color against our color chart, we found out that the pH of this solution is 8.5. The pH of this solution is 8.5. This indicates that sodium acetate aqueous solutions are basic or alkaline in nature. This is due to the fact that sodium acetate can be formed when a strong base is reacted with a weak acid. Strong base sodium hydroxide, when reacted with acetic acid, you form sodium acetate. So the salt that is formed has basic properties. Then we took ammonium acetate. Ammonium acetate, when added with universal indicator, turned to a greenish color yet again. And when we compare this color with the universal indicator color chart that is provided to us, we found out the pH of the ammonium acetate solution is 7. This indicates that the ammonium acetate solution had a neutral pH. Then we moved on to zinc chloride. Zinc chloride, when added with universal indicator, produced a yellow color. And when we compared this yellow color against our color chart, we observed that the pH of the zinc chloride aqueous solution was 6.5, indicating that zinc chloride solution was an acidic solution. So zinc chloride is an acidic solution with a pH of 6.5. Then we move on to ammonium chloride. We can see here, when we take small amount of ammonium chloride and when we add a pH indicator, universal indicator to it, the ammonium chloride aqueous solution turned to a bit of an orange color. And when we compared this orange color against the color chart that we have here, we noticed the pH of this ammonium chloride solution is 5.5 or close to 5.5 in pH. So this indicates that ammonium chloride is acidic. Ammonium chloride is acidic. Then we moved on to aluminium chloride. Aluminium chloride, when added with universal indicator, produced a red color. This red color, when compared against our color chart, indicated that the pH of aluminium chloride aqueous solution is 4. So pH 4 is an acidic pH. It's a bit of a strong acidic pH, indicating that aluminium chloride is somewhat more acidic than all the other acidic solutions that we have here. Aluminium chloride is an acidic solution. And finally, we moved on to magnesium sulfate. When we dissolved magnesium sulfate in water and when we added universal indicator to it, we observed the color that is produced was a green color. And when we compare this green color against our color chart, we notice the pH of magnesium sulfate is 7. So pH 7 is a neutral pH. So magnesium sulfate aqueous solutions are neutral solutions. With that, students, we observed how different aqueous solutions can be acidic, basic, or neutral. Students, with that, we have concluded our experiment 35. In experiment 35, we observed how different solutions can have different pH values, and based on their pH values, how we can determine whether they are acidic, basic, or neutral. So now, let's move on to our studio again to discuss more theory parts and questions revolving around this experiment.
Now students, we are back in the classroom. So let's take a look at some questions that are related to the experiment number 35. So the first question, explain why chromium chloride aqueous solutions are acidic. Now students, if you take chromium chloride, when you have a chromium chloride solution, the CrCl3 that we write over here as aqueous is actually
fully dissociating to produce chromium 3 plus aqueous ions and chloride ions. And students, these chromium aqueous ions, chromium 3 plus aqueous ions that are present in the medium are actually present as hexaquachromium 3 ions. So basically, you will see that with each chromium 3 plus ion, there will be 6 water ligands present. However, students, these chromium 3 plus ions, when they form this complex ion, they actually can deprotonate one of the water ligands and release H plus. So this complex can undergo deprotonation and can obtain this equilibrium where chromium is now in touch with an OH minus ion and 5 water ligands. Earlier it was all water ligands only, but now we have 5 water ligands with 1 hydroxide ion are bonded through a coordinate bond to chromium 3 plus. So now it's 2 plus over here because there is a OH minus along with 3 positive charges coming from chromium 3 plus. So the overall charge is plus 2. So now students, this is AQ. Along with that, an H plus is removed. So due to this deprotonation that has happened, deprotonation in the sense, the water ligands that were present earlier, out of that, one of the water ligands have lost an H plus and turned into a OH minus ion. Now that OH minus ion is still bonded to this chromium 3 plus through a coordinate bond, and the H plus ion that was produced is now released into the aqueous medium. So the H plus ion concentration in the aqueous medium increases. So this is one of the reasons why the chromium chloride aqueous solutions are going to be acidic. This is the reason the chromium chloride aqueous solutions are acidic. So this is something you have to keep in mind. Due to the deprotonation of the water ligands that is attached to chromium 3 plus ions when forming the chromium water complex, we can produce H plus ions. So another very important detail that you can keep in mind is that when it comes to D block element cations, right? So we can write the cations formed from D block elements. D block elements. The elements that we consider are scandium, titanium, vanadium, chromium, manganese, iron we have ferrous, Fe2 plus, Fe3 plus, cobalt, nickel, copper, and zinc. So when considering these ions, there are salts that are produced with anions coming from strong acids. So those salts are going to show a slight basicity when they are dissolved in water. So salts that are produced with these cations along with anions that are coming from strong acids like HCl, HBr, HI,
we have chlorate, perchlorate, nitric, sulfuric. So anions that are coming from these strong acids along with these cations, when they form salts, aqueous solutions of these salts tend to be slightly acidic. So we can write the salts or salt solutions of above cations and anions from strong acids tend to be slightly acidic. So students, so basically strong acids that we consider here are things like HCl, HBr. So we will write the anions that are coming into the medium through them. So through HCl we have these anions. Example, these anions are the ones that we have to consider. Chloride, bromide, iodide. We have sulfate, nitrate. Apart from that, we can also consider things like chlorate, ClO3 minus, or perchlorate, ClO4, ClO4 1 minus. So these kind of anions, when they are coupled with these D block cations, the salts that are formed, when they are dissolved in aqueous medium, they are going to produce a slightly acidic solution. So salts of these cations along with these anions, or salts that are produced with these cations and anions, are going to be slightly acidic when dissolved in aqueous medium. So something that you need to keep in mind. So students, with that, we can move on to the next part of this question. State whether the following compounds are acidic, basic, or neutral. Acidic, basic, or neutral. So students, when it comes to talking about acidic, basic nature of a salt, that is very important to keep in mind. If the salt is produced as a result of a strong acid reacting with a strong base, then the produced salt is going to be neutral. So if you take a strong acid, reacting with a strong base, it produces a salt. So we now know that the salt is going to be neutral, so I will write it as neutral. And water. So students, the salt that is produced here, as I mentioned, is neutral. If you take an example, if you take a strong acid like HCl, react with a strong base like sodium hydroxide, they will react together to form sodium chloride. And you know sodium chloride is a neutral. Sodium chloride is a neutral salt. Right? So if you want to include the state symbols, HCl aqueous, sodium hydroxide aqueous, salt is also going to be aqueous in this case, and water is going to be a liquid. So students, the sodium chloride salt that is formed here is neutral. And why is it neutral? What is the reason for it to be neutral? So sodium chloride salt that is produced over here is in fact present in the medium as sodium ions and chloride ions, right? So they are fully dissociated and they are present in the medium as sodium ions and chloride ions.
And in water, we can see an equilibrium where water dissociates to form H plus ions and OH minus ions. Now, none of the ions that are produced here are going to have any interactions with this equilibrium. So these ions are not reacting with anything here in this equilibrium. There is no reactions observed when it comes to sodium ions or chloride ions. Now, sodium ions are produced from a strong base, chloride ions are produced from a strong acid. None of these are going to react with water and carry out a further reaction. So therefore, students, the pH of water, or the equilibrium that you see over here in water, is not disturbed. Because of that, students, there is no acidity or basicity revolving around salts that are formed when a strong acid and a strong base is reacted. However, we can't say the same about strong acid, weak base, or weak acid, strong base related salts. So let's take a look at weak acid and a strong base reaction. So now, students, if you take a strong base and a weak acid, we'll write the weak acid first. Weak acid plus a strong base, right? Weak acid plus a strong base, we will produce a salt and water. Now, students, we say when a weak acid and a strong base reacts, what we produce is having the characteristics of the stronger reactant here. So out of these two, we say we are reacting a strong base with a weak acid. So the stronger character comes from the base. So that's one way of remembering what kind of nature the salt would have. So salt is going to be basic, right? So this is a basic or basic salt, right? That's one way in which you can remember what type of salt that is. So if we carry out a reaction between weak base and a strong acid, out of these two, the stronger component is the acid. So the salt that is produced is going to be an acidic salt. Apart from that, H2O is also produced. Now I will talk about examples of both of them. Now, if you talk about strong acids and weak bases, we can take an example like ammonia and HCl reacting together. So if you take ammonia, NH3 aqueous, reacting with HCl aqueous, you are producing ammonium chloride, NH4 Cl aqueous, along with water, H2O. So because of this, now we have produced this, because of this reaction, we have produced ammonium chloride salt. Now, ammonium chloride salt is dissociated in water actually. It is present as, although we write ammonium chloride like this, in actuality, it is present as ammonium 1 plus ions, NH4 plus ions in water, along with Cl minus ions, right? So these ammonium ions, they do have an equilibrium in water. They have an equilibrium in water. It can be written in the following manner.
So if you take ammonium ions in water, they can undergo, they can actually establish this particular equilibrium where they turn into ammonia aqueous along with H plus aqueous. Now students, you can see H plus ions are coming into the medium. H plus ions are coming into the medium. Sometimes we write this equation along with water. Ammonium ions reacted with water are forming ammonia and H3O plus, H3O plus. So either way, we can see there is an addition of H plus into the medium due to the establishing of this particular equilibrium that we see over here. So H plus ion concentration in the medium will slightly go up. Now this is not a full dissociation, this is a partial dissociation, that's why we have this equilibrium sign over here. So students, this reaction is going to release certain number of H plus ions into the medium, making the medium slightly acidic. So if you have ammonium chloride salt dissolved in water, if you take a small amount of ammonium chloride and dissolve in water, that solution is not neutral. That solution is going to be acidic because you are producing H plus ions in the medium, and the medium tends to be acidic. And apart from that, if you take a strong acid, weak base type of reaction, right? Strong acid, actually strong base, weak acid, strong base plus weak acid type of reaction. You can see we form a salt which is a basic salt, right? We say it's a basic salt plus water. Over here, when it comes to the strong base, if you take something like sodium hydroxide, and for the weak acid, we can take weak acid like acetic acid, let's say CH3COOH, acetic acid, or ethanoic acid. The salt that is formed over here is sodium acetate, or the IUPAC name will be sodium ethanoate, CH3COONA aqueous, along with water. We can write this as an equation. Aqueous. So the salt that is formed here, this is ionic compound, so although we write it as CH3COONA together, in reality we know this is dissociated to forming CH3COO minus ions in the aqueous medium along with Na ions in the aqueous medium. And this acetate anion or ethanoate anion can show an equilibrium with water. So these anions, weak acid anions and strong acid cation or weak acid cations like ammonium ions, and when it comes to weak acids, the anions can show equilibrium with water. H2O here, we'll see when they react with H2O, we will see that it is producing this carboxylic acid along with OH minus. So OH minus is now introduced into the medium, students. OH minus is now introduced into the medium, so therefore OH minus ion concentration will go up due to this equilibrium. So do you see, when it comes to weak acids or weak bases, when they form salts, when they react with strong acids or strong bases, they form salts, the anion coming from the weak acid and the cations that may come from the weak base will interact with water and establish an equilibrium while releasing H plus or OH minus. So strong acid, strong base salts will never do this. But when it comes to weak acid, strong base reactions or strong acid, weak base reactions, the salts that are produced are going to be showing some sort of alkalinity or acidity. So when it comes to a weak acid, strong base reaction, the anion coming from the weak acid can react with water and release OH minus. So the medium is going to have a higher OH minus concentration, resulting in medium being basic. So that is why we say when a strong base reacts with a weak acid, the salt that is produced is going to be a basic salt. Strong base with a weak acid forms a basic salt that we observed firsthand here. Alright students, so that is something you need to keep in mind. So now students, after going through this part, we can answer these questions over here. So over here we have sodium sulfate formed. So sodium ions, they come from a base, sodium hydroxide. Sulfate comes from the acid. So normally when it comes to a salt, the negatively charged anion comes from the acid and positively charged cation comes from the base. So over here, sodium would have come from a strong base, sodium hydroxide, and sulfate came from sulfuric acid, which is also a strong acid. So strong acid, strong bases produces neutral salts. So the answer is neutral. Now sodium bromide. So sodium bromide would have been formed with sodium hydroxide and HBr. Now HBr, HI, HCl, nitric, sulfuric. Apart from that, perchloric, chloric acids. These are strong acids, right? These are strong acids. So here with sodium and HBr, what we have here is strong base, strong acid reaction, sodium hydroxide and HBr, producing a neutral salt. So the salt that is produced here is neutral. And then we can very clearly see here, we have a weak acid anion, which is the acetate anion or ethanoate anion. So sodium ethanoate is present here. So the ethanoate anion, the negatively charged part of this salt, came from a weak acid. So weak acid was reacted with sodium hydroxide when producing this salt. Sodium hydroxide is a strong base. Ethanoate part came from a weak acid, ethanoic acid. So therefore students, this salt is going to be a basic salt because a strong base reacted with a weak acid. Strong base, weak acid produces salts that are basic in nature. So therefore, when it comes to this, the answer is basic. So students, after sodium ethanoate, we move on to sodium phosphate. So sodium phosphate, sodium comes from sodium hydroxide. Phosphate group comes from phosphoric acid. Sodium hydroxide is a strong base. Phosphoric acid is a weak acid. So strong base, weak acid is going to produce a basic salt. So this is going to be a basic salt. We have calcium bromide, calcium hydroxide, strontium hydroxide, barium hydroxides. These are going to be strong bases, right? Potassium hydroxide, sodium hydroxide, they are all very strong bases. And we have HBr. So basically, like I mentioned here earlier, HBr, HI, HCl. We have, apart from that, sulfuric, nitrate, right? Chlorate, perchloric acid, right? All of these, perchloric acid, chloric acid, all of these are going to be strong acids. And so therefore, the reaction over here is between calcium hydroxide and HBr, between a strong base and a strong acid. So therefore, the resultant salt is going to be neutral. Here we have a weak acid anion and strong acid cation, barium. So this is a reaction between a strong base and a weak acid producing barium ethanoate, which is a basic salt. So therefore this is going to be basic, right? Barium hydroxide is a strong base and ethanoic acid is a weak acid. So strong base weak acid produces a basic salt. Ammonium sulfate. So ammonia is a weak base and sulfate group comes from sulfuric acid. Sulfuric acid is a strong acid. So this is a reaction between a weak base and a strong acid. So the resultant salt is going to be acidic. Weak base, strong acid, and the resultant salt is going to be acidic. So the strong character is going to determine, or whatever the acid or the base which is going to be strong is going to determine the nature of the salt. If the acid is the one that is strong, then the salt is going to be acidic. If the base is the one that is strong, then the base is going to determine the nature of the salt here. So it will be a basic salt. So you can remember it like that, right? So this is just a way that you can remember the nature of the salt that is produced. So a strong acid and a weak base produces a acidic salt. So let's move on to the next one. Right, so over here we have ammonium nitrate. So again, ammonia is a weak base. Nitrate comes from nitric acid, which is a strong acid. So this is a reaction between a strong acid and a weak base. So this resultant salt should be what? A acidic salt. So this is acidic. Potassium nitrate. Now potassium comes from potassium hydroxide. Nitrate comes from nitric acid. Potassium hydroxide is a strong base. Nitric acid is a strong acid. So this is a reaction between strong acid, strong base. So the resultant salt, potassium nitrate, is neutral. Then we have sodium sulfide. Sodium sulfide. So sodium comes from sodium hydroxide, which is a strong base. And sulfide ion here had come from an acid like H2S, hydrogen sulfide. Now, hydrogen sulfide is not a strong acid, it's a weak acid. So the reaction here is between a strong base sodium hydroxide and a weak acid hydrogen sulfide. So strong base weak acid will produce a basic salt. This is a basic salt. And then we have ammonium chloride. Ammonia is a weak base. The chloride ion came from HCl. So this is a strong acid. So weak base ammonia reacts with strong acid HCl. Weak base strong acid produces acidic salt. Weak base strong acid. So acid is the one that is strong. So the salt is going to be acidic. So we have cesium iodide. So cesium is again coming from cesium hydroxide, which is a strong base. Iodide comes from Hi, which is considered a strong acid. So therefore, students, this is going to be a reaction, salt produced through a reaction between a strong acid and a strong base. So the answer is going to be a neutral salt. Sodium cyanide. Sodium comes from sodium hydroxide, cyanide comes from HCN. HCN is not a strong acid. So therefore, it's a reaction between a strong base and a weak acid. Strong base and a weak acid. So therefore, the salt is going to be basic. Strong character is coming from the strong base. Oh, sorry, basic character is coming from the strong base. That's something you can keep in mind. Now, that is not how the reaction takes place. You should remember there are equilibriums that are at play here. But when you're trying to remember whether the salt is acidic or basic, you can think, since we're reacting a strong base and a weak acid, since the strong part is the base here, the salt is going to be inheriting that part, and therefore the salt is basic. That's just another way of remembering what type of nature the salt would have, right? But you have to keep in mind the actual situation is different to that based on the anion that is produced. Anion can acquire different equilibriums with water, releasing OH minus OH plus. In this case, cyanide group reacts with water and obtains an H plus, releasing OH minus. That is why the medium is going to be basic, right? So, but keep in mind, when you are just trying to determine whether a salt is acidic or basic, you can just take a look at what are the two reactants. What is the acid, what is the base that is reacting, which one is stronger, and based on the stronger reactant, you can attribute an acidity or basicity to the salt, right, students? So keep in mind, if a strong base reacts with a weak acid, salt is going to be basic. If a weak base reacts with a strong acid, the salt is going to be acidic. So FeCl3, we learned earlier onwards. Now here Cl3 comes from a strong acid, and Fe or 3D elements, especially when they are forming salts along with the anions of strong acids, the aqueous mediums of these salts are going to be acidic. So the salt over here is very clearly acidic. Copper sulfate, again another ion coming from the D block of elements. So sulfate ion is coming from a strong acid, so this is also going to be an acidic salt, right? So let's move on to the next part. So when it comes to talking about these set of compounds that we have over here, we have nickel and nitrate. Nitrate is a strong acid and ion, and nickel is a D block element. This is definitely going to be acidic. And then we have zinc perchlorate ion. Perchlorate is an ion from a strong acid, and zinc is a 3D element. So therefore, this is acidic. Barium perchlorate. So perchlorate comes from perchloric acid, and you have barium coming from barium hydroxide. So these are all strong bases and strong acids. So therefore, the resultant salt is neutral. Chromium sulfate. Chromium again is a 3D element. We have sulfate, which is an ion coming from a strong acid. So the answer is an acidic salt. And we have ferrous sulfate, the same as the above details that we have discussed. Sulfate is coming from a strong acid, and ferrous is a 3D element. We looked at this in the initial bits of this first question. So therefore, ferrous sulfate solutions are going to be acidic in nature. Cobalt chloride is also going to be acidic in nature. They are slightly acidic when they are in aqueous medium. Lithium fluoride. So lithium is coming from lithium hydroxide, which is going to be a strong base, and fluoride is going to be a weak acid, right? Or coming from a weak acid, HF, hydrogen fluoride. So therefore, students, this is a reaction between a strong base and a weak acid. So the resultant salt, lithium fluoride, is going to be basic. And over here we have a weak acid anion and strong acid cation. So strong base cation. Weak acid is CH3COO minus, which is the ethanoate anion, and potassium hydroxide has introduced potassium ions into this salt. So therefore, students, what we have over here is a salt that is produced through the reaction between a strong base and a weak acid. So the salt that is produced is basic. So these are the answers to this question. I hope by now you have developed a good understanding of how these strong acids and strong bases react to produce neutral salts. Weak acid, strong bases produce basic salts, and strong acids, weak bases produce acidic salts. So you have to keep this in mind, students, because when determining whether a salt is acidic, basic, or neutral, these details are going to be important. At 25 degrees Celsius, the Kb value of ammonia solution is 1.8 moles per decimeters cube. Calculate the pH of an ammonia solution with 0.2 moles per decimeters cube concentration. So these are important details. The ammonia solution has a concentration of this much, right? And the Kb value for ammonia is this at 25 degrees Celsius. Now, you know these equilibrium constant, they are sensitive to temperature. So that's why the temperature is given here, right? So first, let's write the reaction. Ammonia, NH3, aqueous, can react with water, H2O, right, liquid, and it can produce NH4 plus and OH minus. Aqueous here also it will be aqueous. Now we can write a Kb expression for this, and in the Kb expression we know the water will not appear in the expression. We have NH4 plus aqueous, product concentration, and reaction concentration here OH minus, aqueous, NH3, aqueous, concentration. So this is our Kb equation, Kb expression. So now students, afterwards, in order to find out they're asking you to find the pH of an ammonia solution with 0.2 moles per decimeter cube concentration. Actually, since we know that this is the Kb value, you can isolate the OH minus concentration and try to find the OH minus concentration there. And then when you're trying to find the OH minus concentration, we will follow a specific number of steps. I will explain them to you as we do this question. And after finding the OH minus concentration, there are two options for you. You can directly find the POH value, and then you can find the pH value. That's the option number one. Option number two would be to find the OH minus concentration, and then using that OH minus concentration, find the H plus concentration. And after finding the H plus concentration, you can proceed to finding the pH. So there are two methods. So let's first take a look at how we solve this question. We will remove this equation from here for the time being, right? So now they say calculate the pH of an ammonia solution with 0.2 moles per decimeter cube ammonia concentration. So we know the initial concentration, right? We say initial concentration. Initial concentration is 0.2 moles per decimeter cube. So this concentration is communicated in moles per decimeter cube. And we haven't, now of course water will be there in excess, no problem there, and we don't have any of these present in the medium, right? So now we will be moving on to the equilibrium, or we can just write change in concentration first. Change in concentration. So when the equilibrium is established, that number of moles will react and will form NH4 plus and OH minus, and therefore the concentrations will change over here. So we can write the concentration change that you see over here. Imagine due to this reaction, X concentration change happened. So therefore over here as well, you can see the products that are produced are going to be produced in X concentration, right? And then since the number of moles that are reacting is going to be 1:1:1 ratio, if X concentration change occurs in ammonia concentration, the product concentrations are going to be also X for each of the products. And then at that point we can write equilibrium concentration. Equilibrium equilibrium concentration is going to be 2 minus x over here. Now, we are not writing anything for water because water's concentration is going to be quite high as we are conducting this experiment in aqueous medium. So that is disregarded here. And so at this point, we can see the x value, the equilibrium concentrations for the reactant ammonia and the two products, ammonium ions and hydroxide ions, are found out, right? We have given them x values, and for ammonia concentration we have written a small expression 2 minus x. So now we can rewrite our Kb expression. Now Kb expression is equal to ammonium ion concentration multiplied by OH minus ion concentration divided by our ammonia concentration. Now at this point, we know ammonium ion concentration is x and OH minus ion concentration is also x. These are all in moles per decimeters cube. So if you want, you can indicate that as well. So moles per decimeters cube multiplied by x moles per decimeters cube. And this is divided by the ammonia concentration at equilibrium, that is 2 minus x moles per decimeters cube. Now that is equal to the Kb value over here. Kb value was 1.8. Kb value was 1.8. 1.8 into 10 to the power minus 5 moles per decimeters cube. So now, students, you can very clearly see how the units cancel off. Moles per decimeters cube here cancels off this moles per decimeters cube unit, and this unit cancels off this. So therefore, you can finally write that 1.8 into 10 to the power minus 5 is equal to x to the power 2 divided by 2 minus x. So now, students, at this point, we can't proceed forward with this 2 minus x, because if you proceed forward with that, you're going to get to a quadratic equation, and solving that would lead you to two different answers which you can't have. So over here, students, it is better to make an assumption that this x value is very, very small. Now, why would it be very small? So if you observe over here, the Kb value is a 10 to the power minus 5 figure. 10 to the power minus 5. Is it a big value or a small value? Now 10 to the power minus 5 is an extremely small value. So if I just read that number out for you, it will be 0.0000018. So you can see there are 4 zeros before getting to the 18 part, right? So this is a quite small value, Kb value. So Kb value being very small would mean that this numerator is quite small and the denominator is quite large. Then only the Kb value will be quite small, right? That means these x values that we have written over here are very small, right? Extremely small. X values are very small. So we can write a small statement here. We can write since the Kb value is very small, two minus x is approximately equal to 2 itself, right? 2 minus x is approximately equal to 2 itself, right? This is x value. When you solve this, you will find the x value. You will see x value is a very small value, right? So reducing a very small value from 2 is going to result in a number like 1.999 something. So that is approximately 2 itself, isn't it? So therefore, students, we make that approximation here. And then we move on to the calculation. Then we write 1.8 into 10 to the power minus 5 is equal to x to the power 2 divided by 2. So you can solve this and write x to the power 2 is equal to 3.6, because we are going to multiply these two now, right? 3.6 into 10 to the power minus 5. And to find the value of x, we have to get the square root of this. This can also be written as follows, right? We can write 3.6 into 10 to the power minus 5, and the entire thing, right? We'll write the minus 5 part clearly, minus 5, and the entire thing is having a power of half, right? So the x value is that. So you can imagine that the x value is extremely small, right? Over here you can very clearly see square root of 3.6 into 10 to the power minus 5. It's a small value. So students, x was equal to OH minus. So that means OH minus concentration is equal to 3.6 into 10 to the power minus 5 to the power half, or square root of 10 to the power square root of 3.6 into 10 to the power minus 5. You can solve this easily if you wish. We will do that, right? So if you jump this decimal place once to the right hand side, right, it will be 36, isn't it? Right? So when you jump it once to the right hand side, this 10 to the power minus 5 becomes 10 to the power minus 6, right? 10 to the power minus 6. So its square root is going to be 6 into 10 to the power minus 3. 6 into 10 to the power minus 3, because 36 is basically 6 to the power 2. 6 multiplied by 6. So 36 is 6 to the power 2. Right? So therefore, square root of 36 is 6. So OH minus ion concentration is quite small. 0.006. Now students, we have found the OH minus ion concentration. From here onwards, you have two options. Now, first of all, when you're writing, the unit should be mentioned, moles per decimeters cube. So students, this is how you would find the OH minus ion concentration. And after finding the OH minus ion concentration, like I mentioned earlier also, we have two main options. You can find the pOH and then proceed to finding the pH through that. Or you can use the Kw equation to find the H plus concentration through the OH minus concentration we have found here. But students, keep in mind, before you proceed any further, to observe whether you have made any mistakes when it comes to calculating this, right? So that is very important, because we are going to be using these values to finding the pH for the second part of this answer. So let's go over what we have done over here. So we have initially written the equation. So equation is written correctly. And then we write the initial concentration, change in concentrations, and equilibrium concentrations. So initial concentration is 0.2 moles per decimeters cube, right? And then we don't have any of these here. And then we have change in concentration minus X. That means X amounts of ammonium ions and hydroxide ions are formed. So no problem there. And then we move on to equilibrium concentration. So equilibrium concentration is the difference between these two, So students, over here there is a small mistake as far as I can see. We have written 2 minus x. Actually it should be 0.2 minus x. It's actually a considerable mistake here, because this is going to be affecting the rest of the equations. That is why we check whether we have done it correctly. So while you are doing a question, this type of things can happen. So always double check your answers. So it is not 2 minus x, it should be 0.2 minus x. So at that point onwards, we have a few corrections to be made, right? So then whenever we have substituted 2 minus x, those parts have to be corrected here. So instead of 2 minus x here, we have to write 0.2 minus x. Here as well, we have to rewrite this part as 0.2 minus x. So this will definitely affect your final value, right? This will definitely affect your final value. Here as well, we have 0.2 minus x, and since x value is extremely small, we can argue that 0.2 minus x remains more or less 0.2 itself. So here it will be 0.2, and at that point, when you multiply 0.2 with 1.8, you're going to get 3.6, but not 10 to the power minus 5. It will be 10 to the power minus 6 there itself. So over here it will be 10 to the power minus 6 when the multiplication takes place, because there is a decimal place here now, right? So the balancing would be slightly more difficult at this point. So we will change all of these values here going forward. We have over here 0.5s, we have to remove them, and even the final answer, you can't have it the way we have written it over here. So we'll quickly correct them. It will be 3.6 into 10 to the power minus 6 here, and then here as well, minus 6 to the power half, and then when it comes to this point, we can't be shifting it to the other side, because it will not necessarily help us here. So therefore students, the best option we have over here, now if I write it as 10 to the power minus 7 and then the square root of that, that isn't necessarily going to get us to an answer easily. So we can actually rewrite our answer here. We can write, when it comes to the OH minus concentration, we can see if you're trying to find the square root of the 10 to the power figure, it will be 10 to the power minus 3, right? And here it will be 3.6 to the power half. So this is the concentration of OH minus, moles per decimeters cube. And if you try to find the POH value for this, now this is the H plus OH minus concentration, Now, since we have double checked, we can move on to finding the POH value. POH value would be equal to minus log OH minus concentration, and we can write minus, and then we have log 3.6 to the power half, and since this is a multiplication, we can write it as plus. When it comes to logarithmic rules, we know multiplication is going to be considered an addition when it comes to turning this expression into a logarithmic value. So it will be log 10 to the power minus 3. 10 to the power minus 3. And then we can rewrite this. It will be minus log
3.6 to the power half plus, instead of plus actually, since this minus plus will solve itself to be minus, will be minus log 10 to the power minus 3. So when I was opening brackets, this minus multiplied this plus and turned into a minus again. So therefore, we can proceed to answer or solve it a step further here. Minus half, we can bring this half value over here. Log 3.6 minus, actually we have minus 3 over here and minus over here. So when you bring this power over here, it will be plus 3. Minus 3 multiplied by minus is going to be plus 3 log 10. So log 10 is going to be what, students? We don't have to write that. Log 10 is equal to 1. So therefore, we just have plus 3 over here. And if you try to solve this, you can find out the value for log 3.6 using a log book. And then half of that value should be taken and subtracted from plus 3. Then you will get your answer. So let's move on to that part now. So log 3.6 is going to be 0.5563, and then we have the 3 value over here plus 3, and when you solve this, it will be minus, because you have to take half of this, 0.27815 and plus 3 over here. So basically, students, we have 3.000 and 0.2781. We'll keep it to just 4 decimal places, right? So it'll be 9 over here, and it'll be 1 and 2 and 7, right? So 2.7291. So let's see if that is the answer. 9 and 1 together will be 10, and 10 here, another 10 over here, yes, and it will come to 3. So we can double check the answers like that, and you are finally getting to the answer. 2.7219. So this is the POH value. This is the POH value, right, students? So this is how you will obtain the answer. POH value. Right. So let's move on to the next step now. So now, students, at room temperature or 25 degrees Celsius, we know POH plus pH or pH plus POH is equal to pKw. pKw. Now pKw is 14. pKw is 14, and we know pH, so we know POH, so we can write pH is equal to pKw minus POH. So at room temperature, the pKw value is going to be 10 to the power, pKw value is going to be 14, and POH value we have found out is 2.7219. So this is going to be 1872, and we have 13 minus 2 is going to be 11. 13 minus 2 is going to be 11. So students, this is going to be your pH value, right? Your final pH value is going to be this. So this is one way in which you can find your answer. This is one way in which you can find your answer. Now this method would be easier for you because you have already found the OH minus concentration. You can quickly find the POH value, and then using this equation, you can get to this value. And apart from that, students, we can also use this equation as well. Now you know water has this equilibrium, and for this equilibrium we can write equilibrium constant. We call it Kw. Kw
is also referred to as the ionic product of water. It is equal to H plus concentration plus OH minus concentration, not plus, it will be H plus concentration multiplied by OH minus concentration. Right? So now, at room temperature, at 25 degrees Celsius, 25 degrees Celsius, we say the Kw value is equal to 10 to the power minus 14 mol2 dm minus 6. So if you know Kw value, now Kw value at this temperature is known to us. If you know Kw value, and earlier on we found the OH minus concentration, so if you know OH minus concentration as well, if you know both of these, can't you find the H plus concentration? You can. So students, if you are attempting to answer the question through this method, you are going to be using this equation where Kw is equal to H plus concentration multiplied by OH minus concentration, and then you can find H plus concentration that way. So basically H plus concentration at that point, we can write an expression for that is equal to Kw divided by OH minus concentration. So this will lead us to the H plus concentration. So after finding the H plus concentration, you can just substitute it to the pH equation minus log H plus concentration, and you will get to your pH value. So students, this is another method that can be used to obtaining the answer. Either way, you are going to be obtaining the same answer over here. pH is equal to 11.2781. 2781. So when it comes to the two methods, there can be a slight disparity between the final decimal places, but you will get to more or less the same answer regardless of the method that you use. Right, students? Now we can move on to the next step. So in the next part of this question, they ask, to 50 cubic centimeters of the above 0.2 moles per decimeter cube concentrated ammonia solution, 25 cubic centimeters of 0.2 moles per decimeter cube concentrated HCl solution was added. Calculate the pH of the resultant solution. Right. We are asked to calculate the pH of the resultant solution. So we have the concentration of the ammonia solution is 0.2, and we have 50 milliliters of that, and we are adding 0.2 moles per decimeter cube concentrated HCl, but we are not adding 50 milliliters. We are just adding half of that volume, which is 25 milliliters. And then we are asked to calculate the pH of the resultant solution. So students, at this point, we can write an equation over here. We have HCl, right, reacting with ammonia. So first of all, we'll write the equation of what happens when HCl and ammonia reacts. HCl plus ammonia reacts to form ammonium ions. I will write them separately, and chloride ions. We from ammonium chloride, but writing them separately would make it easier for us to understand the effect of the addition of HCl. Right? So apart from that, students, we also have ammonia in the medium. So ammonia in the medium, let's say before addition of HCl, ammonia in the medium would react with H2O, and would form this equilibrium, NH4 plus
and OH minus. All right. So in the beginning, we had 0.2 moles per decimeters cube concentrated ammonia, and we had 50 cubic centimeters of it. We had 50 cubic centimeters of it. So if I just write down what happened over here, we had 50 cubic centimeters of ammonia, right? 50 cubic centimeters of ammonia, right? It was 0.2 in concentration. So to indicate molarity, I will write capital M. And we are adding 25 cubic centimeters of 0.2 m HCl, which will result in forming a new solution. Now, new solution has an overall new volume. Why? Because we are adding 25 cubic centimeters of HCl, so the overall volume is going to be 75 cubic centimeters now. Don't forget, right? So this solution now contains a small amount of ammonia, not small amount of ammonia, certain amount of ammonia that is still remaining, still unreacted. And apart from that, it will also contain ammonium ions and chloride ions. So I'm just writing only the ions that are of interest to us. So this contains significant amount of ammonium ions now, along with remaining ammonia. So you have to keep that in mind. So if you go back to where we were, we can write now the initial number of moles of everything that was present here. So we can write here initial number of moles. Initial amount over here is, now we can convert the number of milliliters that are introduced into the system, or number of milliliters of ammonia solution into moles. We have taken 0.2 moles per decimeter cube concentrated ammonia, and we have taken 50 cubic centimeters of it. So we can easily convert this into number of moles. So we can multiply the concentration 0.2 by the volume. So 50 cubic centimeters can be written as decimeters cube. So 50 divided by 1000. So this is the initial number of moles of ammonia that was present in that 50 cubic centimeter volume. So water was of course there. It was there in excess. So then this is almost a constant. So we don't talk about the concentration of water here. And we didn't have any ammonia or hydroxide ions specifically coming from this reaction, right? Due to water's dissociation, the hydroxide ions are there, but in this case, we are mainly talking about hydroxide ions that can be taken into consideration when considering this equilibrium, right? So this is the initial number of moles of ammonia, and then it can undergo dissociation and form ammonium ions and hydroxide ions, but we know we initially didn't introduce any ammonium ions into the medium. So this is going to be 0 initially. But as the reaction proceeds and equilibrium is established, you will have a certain number of ammonium ions and hydroxide ions coming into the medium due to ammonia establishing this equilibrium. So since we are not here to talk about the initial pH or initial pOH value of this particular solution, we are not going to be looking at that now itself. We are mainly focusing on what happens when HCl is added. So then we can move on to what takes place when HCl is added. So students, when HCl is added, we can see this reaction takes place. And the reaction happens in 1:1 ratio, and this is not a reversible reaction. It's a forward or unidirectional reaction where you produce ammonium ions and chloride ions. So we are adding exactly 0. So we can write the number of moles of HCl over here. We are adding 0.2 multiplied by 25 cubic centimeters, but we have to convert in decimeters cube. We have to divide by 1000.
So this many moles of HCl is added. So along with this many moles, a similar number of moles, the same number of moles of ammonia is going to react, right? 0.2 into 25, the same amount of ammonia is going to react. Since I have not solved this, I wrote the same number here. And when they react in these numbers, the same amount of ammonium ions and chloride ions will be produced. So students, after the addition of HCl, right, we can write the reacted amounts of ammonia and produced number of moles of ammonium ions over here as the amount of change that took place. You can write change in amounts or number of moles of reactants and products. Change in amounts. So over here, we initially had this much, and as I told you earlier, we're adding this many moles of HCl. So along with this many moles of HCl, the same amount of moles of ammonia is going to be reacted. So I can write minus 0.2 into 25 into 25 divided by 1000. This many moles of ammonia is reacted, and at that point we can see the same amount. Now earlier also the medium can have a certain amount of OH minus ions, so OH minus ion concentration is not clearly known to us, so we will leave it be. We'll mainly focus on ammonia and ammonium ion concentration here. So over here we have 0.2 into 25 divided by 1000 many moles of ammonium ions produced. So at this point, students, we have a significantly high amount of ammonium ions and OH minus, so ammonium ions and ammonia here still, even at this point. So if you write at equilibrium, the number of moles, it will be the difference between these two. So it will be basically 0.2 into 25. You can see the rest is the same. So when you find the difference, you can see these two numbers are the only ones that are not the same. Others are common factors, so you can remove them out and subtract 25 from 50. You are getting to 25. So this is the number of moles of ammonia that is remaining in the medium at equilibrium, and the same number of moles of ammonium ions will be formed at this particular equilibrium due to the addition of HCl and forming ammonium ions. Right, students, so all this while keep in mind there is some hydroxide ions produced alongside this, but even before that there was a certain amount of hydroxide ions in the medium. So that is why we haven't written the hydroxide ion concentration here, but or number of moles here. But if you wish, you could have attributed a value for the number of moles of hydroxide ions as X here, and then when this many moles of ammonium ions are getting produced, X plus the same number of moles of hydroxide ions will be present here. And see here also X plus the same number of moles of hydroxide ions. So since we don't very clearly know the total hydroxide ion concentration over here, we'll leave it blank. But at the same time, you have to understand that at equilibrium, the ammonia and the ammonium ion number of moles is the same. Right? While you keep that in mind, we can move on to the final equation. So you can write this particular expression. So they're asking you what is the pH. They're asking you in this case, what is the pH of the resultant solution. So we can find the pH in the following manner. We can write Kb for this dissociation of the base. Kb is equal to concentration of ammonium ions, concentration of ammonium ions multiplied by concentration of hydroxide ions. Now, I told you earlier, concentration of hydroxide ion is not known to us. We don't know, right? And then here, concentration of ammonia is there. Concentration of ammonia is there. And we saw the number of moles of ammonia remaining in the medium at equilibrium and the number of moles of ammonium ions present in the equilibrium is the same. Number of moles of ammonia and ammonium ions that are present in the medium is the same. And the volume is also known to us, 75 cubic centimeters final volume. So each of these numbers are divided by the same volume. So therefore, if the number of moles are the same and the volume that they are divided by is the same, the concentrations happens to be the same. So you can state that over here. And after you state that, you can say, well, first of all, we can say over here, we'll write that as a sentence here. After the addition of 25 cubic centimeters of 0.2 moles per decimeters cube HCl, the amount of NH4 plus ions formed in the medium is equal to the remaining ammonia in the medium. Since both NH4 plus ions and ammonia are present in the same volume, and since they have the same number of moles, the concentrations are the same. So therefore, students, we can then write, therefore, when you write this Kb expression about ammonium ions concentration and OH minus ion concentration divided by ammonia concentration. We just mentioned that these two concentrations are the same. So therefore, this concentration cancels out this concentration. We can write, therefore, Kb value is equal to the OH minus ion concentration. Kb value is equal to OH minus ion concentration. So at this point, we can proceed to finding the answer. So the Kb value we can obtain from the previous part, because this is the second part of the same question. So we know Kb value is 1.8 into 10 to the power minus 5.
So we can just write OH minus concentration is equal to 1.8 into 10 to the power minus 5 moles per decimeters cube. Then you can go through the POH method and get to the answer. You can go through the POH method and get to your answer. Right. So we can convert this into POH value minus log OH minus concentration. Now, since you know how to solve this equation step by step, we can directly get to the answer here. So I will write the answer here. So when you solve this, you get to 4.7447. And then we can write this equation, pKw is equal to pH plus POH. pH plus POH. And then at that point, we know the POH value, we know the pKw value, and then we can write pH is equal to pKw minus POH. So the answer would be 14 minus 4.7447, which would give us the answer 3, 5, 5, 2 over here, and then we have 9. So the final answer that you get is 9.2553. 9.2553. This is the pH value of the solution. Now students, when it comes to writing this pOH value, you can obtain this pOH value with the use of deriving an equation as well, right? So we have this equation where we write Kw or Kb is equal to NH4 plus concentration and OH minus concentration divided by ammonia concentration, right? So we can multiply each of these. We can multiply each of these statements, or we can first of all isolate OH minus first. We'll try to do that, right? So if I do that, I will write OH minus ion concentration is going to be equal to Kb, and then you have to send it over here, so it will be NH3 divided by NH4 plus. And afterwards, students, you can proceed to multiplying all the terms with minus log. So when you do that, the resultant equation is minus log OH minus concentration, and when you do that minus log, we have Kb, and this is a multiplication, so we'll keep this entire term without separating it into two. We'll keep this part together. So Kb multiplied by this term. So since if I keep the minus outside, according to our logarithmic rules, multiplication is going to be written as an addition here. Log NH3 concentration divided by NH4 concentration, NH4 plus concentration. So if you take it a step further, it will be minus log Kb. So minus plus is going to be minus here, log NH3 divided by NH4 plus concentration. Over here we have minus log OH minus concentration. So students, by now you should know that whenever you write pH also, we have this minus part, right? pH is written as minus log H plus concentration, right? So this minus log part is what is referred to as the P in the pH term, and the H plus concentration is referred to as H here. So the use of P here indicates multiplying whatever that we have over here with minus log. So what you have produced when you do that over here is, this part is P and we have OH, so we have produced POH. And again, minus log part is referred to as the P section of this equation. So minus log is P and we have Kb, so this is PKb. And then minus log. Now this part we don't necessarily write it as this in this method, right? So we just write log minus log minus log. We have to write NH3 concentration divided by ammonium ion concentration. So either way we are getting to the same answer, because if you observe over here, in the previous part I explained, after addition of the HCl, the ammonia concentration and the ammonium ion concentration in the medium was equal to one another. So what happened? These cancel off. So when these cancel off, it will be log 1. So log 1, students, is 0. Log 1 is 0. So that means we can write one final step here. POH is equal to PKB, which essentially was the case earlier, right? We saw over here when we were finding this equation as well, right? We found Kb is equal to OH minus concentration. So if you just multiply both by minus log, you are turning Kb into PKb and OH minus concentration into POH. So PKb is equal to POH. You can see it here as well as over here. So basically both of these methods can be used to arrive at the OH minus or the P or OH value, and then we can, through that we can move on to our pH value. Right, students. So now with this we can move on to the next question. When 1 cubic centimeter of 0.2 decimeters cube concentrated HCl or sodium hydroxide is added to the solution formed above in B, will there be a change in pH? What an odd question to ask. We are adding acid or a base into the solution. Why wouldn't there be a pH change, right? So you have to think. Explain with the use of relevant equations. So we have to explain now if there is a pH change, and if not, why? So students, the reason for asking such a question over here is because when we have a base and its conjugate acid, or acid and its conjugate base together in a mixture, we form something called a buffer solution. A buffer solution. So basically, students, we will write this equation again. We have ammonia reacting with water, right, producing ammonium ions along with OH minus ions, right? So this is ammonia, this is the base, and the cation that is formed from the base, or we can just say this is the base and this is the conjugate acid of that base. Conjugate acid of that base. So these two are the conjugate acid base pair, right? Base and the conjugate acid, right? So because if you're talking about the forward direction, you can see it is accepting a proton and acting as a base. But if you're talking about the reverse direction of this equilibrium, ammonium ions are releasing an H plus.
So releasing of H plus is categorized as the action of an acid. So this is acting as an acid in the reverse direction, right? So therefore we call this a conjugate acid of ammonia base. So now students, after figuring that out, we know a buffer can be made with a base along with its conjugate acid in the same medium, or acid and its conjugate base in the same medium. So acid with its conjugate base or a base with its conjugate acid can make a buffer solution. So then why are they asking, when we add a little bit of acid or the base, or strong acid or strong base, what will happen to the medium? Now students, in the medium over here, this is actually in our buffer solution. It's a buffer solution. Now buffer solutions are solutions that can resist the changes in pH when small amounts of acid or base is added to the medium. So if you take a buffer solution and add a few drops of acid or a few cubic centimeters, or let's say a few drops of the base or a few drops of acid, the pH of the buffer does not change. When a small volume of acid or a base is added to a buffer solution, the pH of the buffer does not drastically change. So we can write over here, we have both ammonium ions, NH4 plus ions, along with ammonia. Both are there. In fact, they are present in equal quantities. And then you can write when acid is added. We can write when acid or H plus is added. What will happen? So we can just write the equation. When H plus is added, we can indicate H plus will be taken up by the ammonia in the medium. H plus will react with ammonia. H plus is basically, we are representing acids here with H plus. So acid will react with the base that is present in the media, which is ammonia, and will turn into ammonium ions. Now these ammonium ions that are produced in the medium will not easily release this H plus, because dissociation of ammonium ion releasing H plus is having a very small Ka value, right? You can see ammonium ions can release the H plus and turn into ammonia and H plus ions, but that will not happen that much. It's extremely low in its Ka value. So therefore, this is not going to release the H plus that is taken in through this reaction. Right, students? So therefore, whatever the H plus that is coming into the medium is effectively taken away through this reaction. So therefore, the added H plus is not going to directly increase the H plus concentration and lower the pH. It will not happen, because added H plus is going to react with the ammonia in the medium and will turn into ammonium ions, and the ammonium ions will not release this captured H plus. They will release only a little bit. They will not fully dissociate to release all of the H pluses. So therefore, students, the H pluses that are coming into the medium are effectively removed from the medium. So therefore, it will not contribute to lowering the pH. And then you can write when OH minus, or when a base is added to the medium. When a base is added, at that point, we can see we have ammonium ions also present in the medium, right? So these ammonium ions can react with OH minus ions to produce ammonia and water. Both ammonia and water, so if especially ammonia is a weak base, it will not unnecessarily react with water and release a lot of OH minuses. So out of all of the OH minuses that are coming into the medium, when they directly react with ammonia and produce ammonium ions and produce ammonia, the produced ammonia is going to not release any OH minuses or a lot of OH minuses into the aqueous medium, because the Kb value for ammonia is very small. So when ammonia is present in the aqueous medium, the release of OH minus that is going to take place due to the presence of this base, additionally that coming into the medium, is going to be very low, right? So over here, all of the OH minuses that are coming into the medium are going to be taken up by the ammonium ions to produce ammonia and water. And the produced ammonia or water are not going to release OH minus ions into the medium that much. So therefore, students, out of majority of the OH minuses that are coming into the medium, only a very little will come back into the medium due to the reaction between ammonia and water. But almost all of the OH minuses that are additionally added to the medium will react and get removed from the medium. So therefore, they are not going to be present in the medium to bring about a pH change. So you can write these equations and then write as seen above. The H pluses or the OH minuses that are coming into the medium are going to effectively be removed from the medium with the use of ammonia and ammonium ions that are present in the medium. Therefore, these H pluses or OH minus ions that are externally added to the medium will not result in a drastic change of pH, right? So that is something you need to keep in mind. So students, just to demonstrate, now that is the answer to the question, just to demonstrate that there is not going to be a huge pH change, we can actually do a small question over here. So students, to demonstrate that this is not necessarily going to change the pH a lot, we can actually use what is referred to as the Henderson-Hasselbalch equations that we have developed even earlier. So we have developed this equation, POH was equal to PKB minus log, we had ammonia concentration here divided by ammonium ion concentration, right? So this was the equation we developed. If you can't remember, we can go back and see, have a look at this. So we have developed that equation here, ammonia concentration divided by ammonium ion concentration. Another version of this equation that we can write is, we can change this plus sign, right? We can change this to plus sign. That means we have to write ammonium ions on top and ammonia at the bottom. And then, so when you invert this, the sign also is going to change from minus to plus. Apart from that, instead of writing it for pH, if you are dealing with a weak acid and its conjugate base, we can write directly for pH. pH is equal to pK A, and then you have a similar portion to this. So you have to derive that and get to the answer. Anyway, if you take a look at this, students, for a given acid or a base, we only have, we only see these two terms governing the POH value. Now, let's talk about a base. So the POH value is governed only by these two terms, PKB and this entire term. And PKB is a constant, isn't it? Constant, right? At a given temperature, this value is a constant. That means the POH value is mainly dependent on the ratio between the base and its conjugate acid, or base and its cation. So if their concentrations alter, when they change, then the POH value will change. And based on the POH value change, the pH is going to change, because pH and POH, they are like a seesaw. When the pH is increasing, POH is decreasing. When the POH is increasing, pH is decreasing. So you have to keep that in mind, right? So over here, students, now if you take an example, earlier we saw that the concentration over here in the original solution that we took was actually, if I just wrote it down over here, the number of moles was given as 0.2, both of their concentrations. I will write it here because I do not want to clutter this area. So if you take ammonia and ammonium ion concentration in the medium of the buffer solution we produced was equal to one another. We knew that, right? It was NH4 plus was equal to 0.2 multiplied by 25 divided by 1000. Actually, I want to get to the number of moles, not necessarily the concentration. So we will talk about number of moles here, because number of moles is what is important. So number of moles of ammonia was equal to the number of moles of ammonium ion. So what I have found over here is the number of moles of ammonia as well as ammonium ions. Right, so this is basically, we can write this as 5.0 into 10 to the power minus 3 moles. Right, 5.0 into 10 to the power minus 3 moles. Now, imagine, now, and we also know the pOH value at that point. So we'll write the pOH value to begin with. It will be easier that way. So they ask us to find the over here we have already found the pH value, and pOH value was also found, right? So at this particular point where the ammonia and ammonium ion concentrations were the same, the pOH value was this 4.7447, and therefore the pH was this, right? So we will note this down. This is very important. So I'll highlight this over here with the red color. This is the pOH and this is the pH. And then I move on to the next part. Over here, now I'm going to take into consideration the fact that I'm adding exactly 1 cubic centimeter of H plus or acid, right? Basically 1 cubic centimeters of H plus ions, H plus ions, and the concentration of the H plus was given to us. So the acid concentration was given to us as 0.2 moles per decimeter cube. In this question, they have asked that, right? So that means we can calculate the number of moles of H plus that is coming into the medium. Number of moles of H plus that is coming into the medium is going to be equal to 0.2 moles per decimeter cube multiplied by 1 cubic centimeter. So if you convert it into decimeters cube, you have to divide that by 1000, which would mean we are adding exactly 0.2 into 10 to the power minus 3 many moles, right? So if you add this to a neutral solution, the pH will drop quite a bit, right? pH will drop to about 3. But over here, when we have this buffer solution, when we have added this, we can see what kind of change in the number of moles of ammonium ions and ammonia ions will be happening. So we know the addition of H plus is tackled by ammonium, as ammonia molecules in the medium. So we have this forming ammonium ions. Now, initial number of ammonium ions is 5 into 10 to the power minus 3 moles, right? Here also we had initially 5 into 10 to the power minus 3 moles, right? So this is the initial moles, initial amount. And then we have addition of HCl.
addition of HCl, that will cause a spike in H plus concentration over here. It will be 0.2 into 10 to the power minus 3. So this amount of HCl is going to react with the same amount of ammonium ions over here. So it will be minus 0.2 into 10 to the power minus 3. And over here, it will cause an increase of ammonium ions. So I will write it as plus 0.2 into 10 to the power minus 3. So when that happens, we can write equilibrium number of moles. Equilibrium number of moles. So equilibrium number of moles is going to be here 4.8 into 10 to the power minus 3. HCl is not going to be there. And we are dealing with, actually, let's say initially we added this much. So basically it's not going to be there anymore after that, right? And then when you have formed this many moles of ammonium ions additionally, the final number of moles is going to be 5.2 into 10 to the power minus 3. So at that point, students, we can see how the number of moles have changed. And if you take a look at their concentrations, basically if you want to get to their concentrations instead of number of moles, we can get to the equilibrium concentrations. Concentrations is going to be it's going to be 4.8 into 10 to the power minus 3 divided by the total volume of the solution. Here also 5.2 into 10 to the power minus 3 divided by the total volume of the solution. So now we can write this equation. POH is equal to a pKa value, or sorry, pKb value in this case, because we are dealing with a base here, minus log ammonia NH3 concentration divided by ammonium ion concentration. Now if you take a look at this, the pKb value remains the same. So we have minus log 10 to the power 1.8 10 to the power minus 3. So we'll just substitute the values over here. Minus log 1.8 into 10 to the power minus 5 minus over here log, we have 4.8 into 10 to the power minus 3 divided by 5.2 into 10 to the power minus 3. Now students, you can solve this equation step by step and get to an answer, right? So when you solve this equation step by step and you obtain this ratio again, and you find the log value for the ratio, and then you have a value for the pKb value over here. So after you find this, you're obtaining this final answer. So this is the final value that you get when you solve this part. And when you try to solve this, you'll first get the ratio, and when you find the log value of that, you'll come to 0.0347. 0.0347, right? So this value is going to be a positive value, because over here for the log value you get a negative value, and then minus minus is going to be positive, right students? So you are going to get to 0.0347. Now students, after obtaining that value, you can add them together. You can see this is going to be 14, and then this is going to be 8 plus 1 is 9, right? And 3 plus 4 is 7, and this is going to be 7. So over here, you can very clearly see that
when you're communicating your pH values, you usually communicate, let's say, up to about 2 decimal places. So originally the pOH value of the solution was 4.7447. So let's say originally pOH value was 4.74. Now it is 4.77. It has only changed from 0.03 of a pOH value. So if you want to find out the new pH value is going to be equal to pKw minus pOH. So therefore, this is going to be 14 minus 4.7794. So therefore, you have obtained this final answer. So it's going to be 6.022, and this is going to be 9. So if you take the solution that you initially formed, right, and the solution that you have formed by adding 1 cubic centimeters of HCl that has a concentration of 0.2 m, right? At that point, we have gone from pH over here, the initial pH was 9.25, right? We have gone from 9.25. Now we know there are other decimal places, but let's communicate it up to 2 decimal places so that you can very clearly see how much of a change this is. 9.25 to 9.22. 9.22. So students, at this point, it has to be very clear to you. The pH change that has happened is extremely small, 0.03 change only. If you take 1 decimeters cube of water that has, let's say, this many moles of HCl. So this many moles in the sense, now imagine you take neutral water. This is also a very important observation. Neutral water, let's say we take 1 decimeters cube, right? It has a pH of what? pH of 7. Now, we have taken here 0.2 moles per decimeters cube. So just to make life easier for us when I'm discussing this, if I take 0.1 moles per decimeters cube HCl, right, and we have added, let's say, 1 cubic centimeters, right? Now, and imagine this will not cause we'll assume that the volume increase is negligible. At that point, students, we basically have in this 1 decimeters cube solution a specific number of HCl moles. Let's say NHCl number of moles is going to be equal to 0.1 multiplied by 1 divided by 1000. This is the number of moles, right? So this many moles is basically can be written as 1 into 10 to the power minus 4. There is 1000 over here, there's a decimal place over here, so 10 to the power minus 4 moles. So since this is present in 1 decimeters cube, the H plus concentration over here is going to be equal to number of moles divided by the volume, 1 decimeters cube. So H plus concentration is 1 multiplied by 10 to the power minus 4 moles per decimeters cube. Now students, you should be proficient enough to convert this into a pH value. pH value, even without equation, you can say the pH is now 4. pH is equal to minus log H plus concentration, and that is going to be minus log 10 to the power minus 4. Minus 4 comes over here, becomes plus 4, and log 10 is equal to 1. So therefore, plus 4 multiplied by 1 is 4 itself. So do you see, even if I add half the number of moles that I have added into our buffer solution, if I add half the number of moles of HCl,
that I have added into the buffer solution into 1 decimeters cube of neutral water, the pH change that we see is massive. It goes from pH 7 to pH 4. 3 whole pH units of a difference, right? pH change, delta pH, is 3. 3 whole pH units have changed. And over here in the buffer solution, when we add twice the number of moles of HCl into the buffer solution, you can see it has changed from a measly 0.03 pH units. Only that. So this is the importance of the buffer solution. So students, with that, we can actually conclude today's question discussion. I hope by now you have developed a good understanding of the questions revolving around acids, bases, salts, and even buffers. So with this, we will conclude our experiment number 35, and I will see you again in the next experiment.